spoilers.
Steal a little of your thunder. I'm also going to mention Dan.
Okay, yeah, you should. Yeah, that's appropriate.
Teach you schematic or no?
Yes, but not any one person.
Okay. Welcome, everyone. Our keynote this morning is by Lindsay Cooper from the University of California, Santa Cruz. We're here at Indiana University discussing functional programming, so it's fitting that I get to introduce an IU alumna and also someone who, like me, was brought into functional programming and into the ICFP community at IU and by our colleague, Dan Friedman. Lindsay attended Grinnell College, where she was first introduced to scheme and functional programming. Subsequently, she studied at IU, where she began by taking Dan's programming languages course, in which she learned how to understand programming languages by writing interpreters. This experience led her into her PhD, working with Ryan Newton, focusing on deterministic, lattice-based parallel programming, pairing well with our lovely keynote by Edward yesterday. Subsequently, she's been a research scientist at Intel Labs and a professor at UC Santa Cruz, where she's worked on topics ranging from choreographic programming to neural network verification to replicated data types. Lindsay is also a prolific organizer and mentor, including creating Bang Bang Con, a conference on the joy and fun of programming, a topic near and dear to all of our hearts here at ICFP. Today, she will tell us about how you can continue to find interpreters everywhere. Lindsay Cooper.
Well, thanks so much, Sam, for that lovely introduction, and hello, ICFP. I am so honored to be here. Thanks to Sam and Manuel for inviting me. Thanks to all of you for being here. This talk is going to feature the work of 4 amazing current and former students, Gan Shen, Shun Kashiwa, Jonathan Costello, and Patrick Redmond. I could not be giving this talk without them, and I only wish that I had time to talk about all of the neat things that they've done. And I also want to thank the audiences who've listened to me give various versions of this talk before, at Indiana University last November, at Northeastern University in January, and most recently at the Choreographic Programming Workshop at PLDI back in June. And if you were there for any of those versions of the talk, I'll try to make it interesting a second time. I want to set the stage with a bit of storytelling, which Sam foreshadowed. And my story, like so many stories, begins with this guy, Dan Friedman. I was a PhD student at Indiana, not here in Indianapolis, but in Bloomington, which is about an hour's drive to the south of here, and much prettier and with more personality. And when I arrived at as a brand new PhD student in 2008, I took Dan's programming languages course, which was at the time fondly known by people at IU as Intro to Dan, and Will Bird, who's sitting right there, was the TA. We called them AIs, though, which stood for Associate Instructor, kind of weird acronym. In this course, you learn what programming languages are made of by writing interpreters. That was how my PhD began. It was how I got hooked on programming languages as a field. So I was there at Indiana for 6 lovely years doing a programming languages PhD, and that journey involved some twists and turns. But long story short, eventually I was working with my advisor, Ryan Newton, on programming language abstractions for writing shared memory deterministic concurrent programs. Now that's not the topic of my talk. Deterministic concurrency was the topic of yesterday's excellent keynote talk. And by the way, if you had told me in grad school that one day, A, I was going to give a keynote talk at ICFP, and B, there would be a keynote about deterministic concurrency, but C, it would not be my talk, then I would not have believed you. But anyway, I worked on monotonic data structures for deterministic concurrency, and it was all about shared memory, or so I thought at the time. But then in the last year or so of my PhD, people who were interested in distributed computing, so specifically not shared memory, tracked me down and said, hey, your work seems to have a lot to do with our work. You ought to look at our work. So as an example of that, here's an email that I received from Mark Shapiro back in 2013. Mark is a distributed systems researcher and one of the creators of something called CRDTs, or conflict-free replicated data types, which are data structures that are used in distributed systems to ensure fault tolerance and high availability. And I got this email from Mark near the end of my PhD suggesting that I take a look at his and his collaborators' work on CRDTs. And of course, he was right. CRDTs were closely related to what I was working on. But to understand CRDTs, I needed to do some other reading on distributed systems. And one thing led to another. And I had kind of a revelation at that point, because up until then, I had really only paid attention to PL research, and I didn't consider what else was out there. But once I looked beyond PL, I realized that the field of distributed systems, distributed computing, is fascinating, and that I had a lot to learn from it. Not only is it practical, it's also brimming with profound and beautiful theoretical results. And so that's when I really began to study distributed systems. And of course, I didn't stop being a programming languages person. PL has always been and still is my research home. But over these last 10 years or so, I've tried to study distributed systems from a programming language person's perspective. And my students and I have been going around sneaking distributed systems ideas into PL conferences. And these papers listed here are some examples from the last 6 years, a couple of which I'll say more about later. But finally, after years and years of this, I had another realization. And this one is going to come as absolutely no surprise for the many people who are here who are part of the Dan Friedman intellectual tradition, which I often like to call the Dan-aspora. And that realization, of course, was that despite my having been on this long side quest into distributed computing all those years, a lot of what my students and I had been doing all that time was still all about interpreters and interpretation. So, oops. So in the rest of this talk, I'm going to talk about a couple of our group's projects that I think exemplify this ultimately unsurprising realization that I had. And both of these projects are about distributed systems, but I'm going to talk about them through the lens of interpreters. So this obligates us to try to answer this question: what is an interpreter? So naturally, the first thing that I did when I was writing this talk was to ask people on Mastodon what they thought an interpreter was. And of course, my friend Ken Sean trolled me by replying with this dictionary definition: someone or something that interprets. Well, that's a true but unhelpful answer. But there was also another definition in the same dictionary that's computing specific. And here's what that one says: a machine that prints on punch cards the symbols recorded in them by perforations, and a computer program that executes each of a set of high-level instructions before going to the next instruction. Okay, well, you tried. I think both of these definitions are pretty bad too. So I think we can do better. So here's my definition. For the purposes of this talk, I'm going to say that an interpreter is something that takes syntax and produces semantics. I like the generality of this definition. It lets us plug in our own notions of syntax and semantics for whatever domain we're interested in. And it doesn't even have to be computing specific. So for example, and this analogy is due to my friend C.F. Boltz, we can think of a choir as an interpreter. Now, this may be a dramatically simplified caricature of what actually happens when people sing together. Trust me, I'm a music major. Do not come at me for this. I still think this is a useful analogy. We can think of the choir's job as interpreting a musical score and ultimately giving it a meaning as audible music. In computing, we might want to think of an interpreter as something that takes a program and produces some kind of value. I'm not going to attempt to nail down a definition of program or value here, but I will point out that the value that you produce might itself also be a program, in which case the last arrow here is a compiler. So at the risk of really annoying the compiler folks here who I respect, I'm going to argue that for the purposes of this talk, a compiler can be thought of as a special case of an interpreter. And I would also argue that every programming language is an interpreted language, because sooner or later, your code is going to run on the CPU, and a CPU is itself an interpreter. So it's interpreters all the way down. But there's another key thing that I want to mention about what interpretation means. If you'll continue to indulge me with this choir analogy, a musical score for a choir will typically have different parts that people sing. And if we say that syntax is interpretable, that usually says something about the form that that syntax takes. In particular, it says something about how the interpretation of a given input is determined by the interpretations of its subcomponents, which are then composed again. And to be able to do this, there should be a way to break down the input into those subcomponents and then put it back together. In other words, it has to be inductively structured data, like an abstract syntax tree. So what I want to do next is dig into a couple of specific places where this notion of interpretation has arisen in my own work these last several years. And I'm going to focus on 2 lines of work from that list I gave earlier: library-level choreographic programming and causal separation diagrams. I won't be getting into all of the details, but if you're interested, I'm happy to dig into them in Q&A or in the hallway later. So let's jump in. Let's talk distributed systems. In the world of distributed computing, we're often concerned with message passing systems. And the idea is that you have some independent nodes that communicate with each other via some kind of network by sending and receiving some kind of messages. They don't share memory, so the only way for them to coordinate is by passing messages. And as a really simple example, let's suppose that our independent nodes are Alice and Carol here. And there's some kind of desired global behavior of the entire system that we want, but somehow Alice and Carol have to accomplish that global behavior by only taking local actions. They can each send messages, they can receive messages, and they can take internal actions, and that's it. Let's say we want to execute an incredibly simple protocol in which Alice sends a request to Carol and Carol responds to Alice. How do we program it? Well, let's assume for now the existence of send and receive functions that actually implement the message transport somehow, whether that's via TCP or via pigeon post. We're not going to concern ourselves with the details of how that transport layer is implemented, and instead we're just going to think about what Alice and Carol do, assuming that the transport layer exists. So for this incredibly simple protocol, Alice might run a node local program like this one on the left. She would, well, let's suppose that receive is blocking. So if you call receive, you sit there waiting until a message shows up. So Alice would send a request to Carol and then wait for a response. And meanwhile, Carol would run her own node local program, which might wait for a request from Alice and process the request in some way, get a response value, and then send that back. This is just about the simplest distributed program that I can think of. But even here, notice how Alice and Carol are utterly dependent on each other to faithfully follow the protocol. For instance, what if Carol forgot to call receive? Even though Carol messed up, it's now Alice's problem. Alice will now wait forever to get a response, or maybe she'll time out and report an error. In general, nodes have to exchange messages in a carefully executed dance. every message sent from a node should be expected by some other node and vice versa. And if one node is running buggy code, then things can go wrong for somebody else. And of course, it only gets more complicated if we add more nodes to the mix. Let's say that Alice is sending Carol a request, and then Carol is supposed to pass the request along to Bob, get an acknowledgement from Bob, and then finally respond to Alice acknowledging that request. In this scenario, Alice might not even know that Bob exists. But nevertheless, if Bob is misprogrammed, then that could mean bad news for Alice. And this example calls to mind this classic quote from Leslie Lamport, in which he says that a distributed system is a system in which the failure of a computer that you didn't even know about can render your own computer unusable. The challenge for programmers, then, is to reason about the implicit global behavior of a distributed system, like Alice, Carol, and Bob together accomplish a task, while writing the explicit local programs in terms of sends and receives that actually run on each node. And that brings us to the idea of choreographic programming, which tries to make that implicit global behavior explicit in the code. In choreographic programming, we don't write the local programs anymore at all. Instead, we write a single global program that's called a choreography. And then we can generate a collection of local programs, one for every node, from the choreography via a technique called endpoint projection. So every choreographic programming language has some kind of operator like this squiggle arrow that you see in the first line of the choreography on the left. This is usually pronounced COM because it denotes communication between two parties. And a COM expression in a choreography expresses both a send and receive at once. When this choreographic program gets projected, every occurrence of, say, Alice on the left-hand side of a COM is going to turn into a call to send on Alice's node. And every occurrence of Carol on the right-hand side of a COM is going to turn into a receive on Carol's node. And we can see the opposite happening on the bottom line, where we're generating a send for Carol and a receive for Alice. Thanks to this mechanism, as long as our endpoint projection is correct, we can rule out the possibility of a mismatched send and receive in the collection of local programs that we generate. And therefore, we can rule out a certain class of bugs. And in a nutshell, that's the benefit of choreographic programming. So at this point, I want to acknowledge an elephant in the room, which is that with what we've shown so far, choreographic programming per se does not do anything to help us should one of these nodes crash or should one of these messages be lost. Those fault tolerance problems were present in the non-choreographic version of the code, and they're just as present in the choreographic version of the code. So choreographic programming by itself doesn't do anything to address that particular challenge of distributed programming. What the choreographic approach specifically gives us is a way to rule out programming errors that stem from mismatched sends and receives. Now, you might think that this would be simple, because if you have two parties like this, it's not a big deal. When one calls send, the other calls receive, and vice versa. But if you have three or more involved, it's not that simple, and that's the setting where choreographies really shine. So let's look at a setting with three parties and with some more interesting control flow. So here's a slightly more interesting protocol. Here's suppose Alice wants to interact with Carol, but she gets stopped by Bob, who wants to check her credentials first. So in this protocol, Alice's credentials have to be verified by Bob before she can interact with Carol. Bob will run this check function on Alice's communicated data. Depending on the outcome, Alice will either receive an access token from Carol or not. So this diagram represents two different ways that this execution could go. To express this in a choreography, we can have conditionals at the choreography level. And here's what that looks like. So on the first line here, there's our squiggle arrow again. This line, alice.credentials squiggle arrow bob.auth request means Alice computes something called credentials, sends it to Bob, who receives it, and then stores it in a variable on his end called auth request. And then we have a choreographic conditional. The conditional check takes place locally on Bob. And then depending on which branch we take, Bob will either communicate success to Carol, who will store it in this variable called decision, and then she'll communicate the token to Alice, or Bob communicates failure to Carol, who will then tell Alice that she can't have the token. What I think is useful to point out about this execution is that even though the execution is spread out across these three different parties, if we think about the execution globally, this is actually a sequential program in which steps happen one after the other. And we can see that from reading the choreography. The choreography looks very straightforward. In fact, it looks remarkably similar to our informal diagram. If we were to write this code as a traditional distributed program, which is really 3 programs running on the 3 participants, the control flow wouldn't be as obvious. And of course, to actually run this thing, we do need to project it. Endpoint projection will take this choreography and turn it into those versions running on Alice, Bob, and Carol, respectively. And this can be done automatically by the choreographic language implementation. And I've written some pseudocode here to show what the projected code might look like for our 3 parties. And like I said, notice how in the projected code, the control flow isn't as clear. You might have to kind of squint at it for a bit to figure out, okay, what's supposed to happen first, what's supposed to happen second, and so on. So one thing that choreographies can also give us, aside from that sends and receives match up guarantee, they can also give us readability. So we didn't invent any of this stuff. Choreographies have been around for a long time. Here is my opinionated and highly personal timeline of the development of choreographic programming. So in the early 2000s, the World Wide Web Consortium's Web Services Choreography Working Group, alongside a group of invited experts from academia, developed a draft specification for a choreographic language. It was called Web Services Choreography Description Language, or WSCDL. Catchy name. The WSCDL language, though, was not intended to be executable. It was only a specification language. Fast forward to 2013. This is when Marco Carbone and Fabrizio Montesi published the core programming language. This language pioneered the idea of an executable choreographic programming language that used endpoint projection to compile choreographies to actually executable node local programs. After that, Fabrizio teamed up with Saverio Gianlorenzo and Marco Peresotti to create the Coral programming language, which was intended to be useful for realistic programming. Coral is here on the timeline in 2020, even though their Toplis paper wasn't published until 2024. They were working on it for many years prior, and 2020 was, I believe, when the first version of the paper showed up on Archive. Coral is designed to be familiar to Java programmers, and the creators of Coral made a point of using object-oriented mainstream programming abstractions, and the Coral compiler projects choreographies to executable Java code. Then, in 2022, my friend Andrew Hirsch and Deepak Garg created a choreographic programming language called Pirouette, which combined choreographic programming with higher-order functional programming. So now you can have choreographies that take choreographies as arguments, which is really cool. This paper made a splash in the functional programming research community. It won a distinguished paper award at Popple that year. It's how I found out about choreographic programming for the first time, my students and I. And it's also notable for its mechanized proof of deadlock freedom. So my student, Gan Shen, read the Pirouette paper, decided that he wanted to try implementing a choreographic language himself. Gan being who he is, the approach that seemed obvious to him was to do it as an embedded domain-specific language in Haskell, in the form of a Haskell library. And what's funny about this was that Gan wasn't even particularly trying to do something novel. He just wanted to learn about choreographies. But it turned out, to our surprise, that the idea of implementing a choreographic language purely as a library hadn't been done before. And this appeared at ICFP 23, where it also won a distinguished paper award. So for a couple of years in there, every PACMPL paper about choreographic programming was getting a distinguished paper award. Sadly, no longer true. So let's dig in a little bit to how Haskell works. In the traditional approach to choreographic programming, which is exemplified here by Coral, you write a choreography in a standalone language, and then you compile it to an executable endpoint, collection of executable endpoint programs using a standalone compiler. This all works fine, but it doesn't mean that you need this purpose-built compiler. In Haskell, on the other hand, choreographies are expressed as programs in an existing host language. In this case, it's Haskell. And the choreographic language construct and endpoint projection are implemented entirely by a host language library without any additional compiler support or any additional runtime support beyond what the host language can already do. In particular, our choreographic language is implemented in Haskell as a monadic DSL using something called a freer monad, which separates the interface and the implementation of effectful computations. By itself, the language doesn't assign any meaning to choreographic operators, like that squiggle arrow, com. It just accumulates them as a big term And then we dynamically interpret that term based on the location where the code is running. So for instance, in Haskell, the COM operator gets dynamically interpreted as send if it's being run at the sender. It gets dynamically interpreted as receive if it's being run at the recipient of a message, and it gets interpreted as a no-op if it's being run anywhere else. So the usual benefits of embedded DSLs that we all know about apply here. Because Haskell choreographies are really just Haskell programs, it means that a Haskell programmer can take advantage of the whole Haskell ecosystem around it. And it also means that it makes it easier to integrate choreographies into bigger non-choreographic systems. There's not a need to change languages and ecosystems just so that you can implement certain parts of your code choreographically. I think this is a big selling point because choreographic programming might be a great fit for certain components of a system, but not others. You might have a system where almost all the computation is local, but maybe there's an occasional short-lived network interaction. And maybe it's doing something that you really want to make sure is correct, like authentication or something. So that's an argument in favor of the library approach to choreographic programming from my point of view. One of the consequences of this library level approach is that endpoint projection actually happens at runtime. So let's take a look at how that works. This is the endpoint projection function's signature in Haskell. And this is just a regular function. It's not a macro or anything. And I hope to convince you that it's really just an interpreter. I promise you that this is the only Haskell code that I'll make you look at in the whole talk. And it's actually just a type signature. Endpoint projection takes two arguments. The first argument is this choreo thing here, which is a choreography. The second argument it takes is a location, which is the place we want to project to, so like Alice or Bob or Carol. And endpoint projection returns something called a network, which you can think of as a low-level program in terms of sends and receives that's been specialized to the particular location you gave as an argument. So for the Haskell enthusiasts here, both choreo and network are freer monads. But we can think of things of type choreo and things of type network as just being programs. And the choreographic operators that are in choreo programs, which are locally conned and com here, these all get interpreted to things like send and receive in network programs. So choreo gives us a syntax for choreographies. And on the network side, I've put semantics in quotes here, because this isn't actually semantics yet. This is still just syntax, and then that will get dynamically interpreted to the actual meaning of send and receive and so forth. What is the actual meaning of send and receive and so forth? Well, that meaning has to be supplied by what we call a network backend. And Haskell comes with a couple of these that you can choose between, and you can also implement your own. For example, there's an HTTP backend that uses HTTP for the message transport. There's a local backend that implements these send and receive functions as communication among threads on a single machine. So that's endpoint projection. It's just an interpreter. So coming back to our timeline, it's exciting to me how after Haskell came out in 2023, a lot more choreographic languages as libraries have popped up. Some of them are from our group. So multicore is a successor to Haskell. Chorus is a choreographic programming library for Rust. ChoreoTS is a choreographic programming library for TypeScript. But what's even more exciting to me is that a lot of these are not from our group. And folks are working on this way beyond our group, both in academia and outside academia. So here's a list. There's CoreCamel for OCaml, which is from one of Anil Madhavapeti's students, and which appeared at the OCaml workshop. There's CoreX for Elixir, which is from Ben Greenman's group at Utah, and which was published last year. There's Clore for Clojure from Lovro Lugovic, who was Fabrizio Montesi's student. There's Coret for Racket, which is from Andrew Hirsch and his group at Buffalo. There's Unicorn, which is a port of Haskell to the Unison distributed programming language. And the most recent one I've heard of is Mooncore, which is for a distributed programming language called Moonbit. All of these are libraries, just like Haskell, but they all do it a little differently, because they're all using the idioms that make sense in their respective languages. So, for instance, Coret is built on Racket, and the Racketeers here will be unsurprised to learn that in Coret, it's done using macros. Likewise, CoreX uses Elixir's macro system. And Unicorn uses a Unison language feature called abilities, which is better known to folks here as algebraic effects. I also want to acknowledge all of the students who have worked with me on library-level choreographic programming, some of whom have their names on this slide. So the Haskell library I mentioned was created by my student, Gan, who was my very first PhD graduate. He defended his PhD in June, and here at ICFP on Monday, he ran a tutorial on hacking choreographic programming in Haskell that some of you attended. The Chorus and ChoreoTS projects were led by my former master's student, Shun Kashiwa, who also contributed to Haskell, and he's a PhD student at UC San Diego now. And that work also led to our collaboration with Mako Bates, who is the creator of Multicore, and who just recently completed his PhD with Joe Neer at Vermont. And I'm really lucky to have worked with all these amazing people. One last thing to mention before I move on to causal separation diagrams is that, to me, the emergence of all of these different choreographic programming libraries in the last couple of years, all of which seem to leverage their host languages in different ways. To me, this points to an interesting research question, which is what language features and abstractions are important to being able to implement choreographic programming in a given language, not only in terms of expressivity, but also efficiency and safety and ergonomics and maintainability. And I asked about this on Mastodon recently, and I got a great response from my friend Ron Garcia, who mentioned that he has also been interested in this kind of research question, and that his most cited paper from UPSLA 2003, a comparative study of language support for generic programming, asked an analogous question about generic programming. He and his colleagues, who are all part of the Dan Aspera, by the way, considered 6 programming languages, and by writing a lot of code in each of them, they studied to what extent each of them supported generic programming. They identified 8 language features that they concluded were necessary, and then they evaluated each of those 6 languages according to how well each of them supported those 8 language features. And by the way, Haskell did the best. So in that same vein, I would love to see a comparative study of language support for choreographic programming, and maybe some of you will be inspired to give it a try. So that's it for the first line of work that I wanted to talk about on library-level choreographic programming. And now I want to talk about another line of work on causal separation diagrams. So let's talk diagrams. People who work on concurrent and distributed computing have been using diagrams like these. I call them Lamport diagrams in the tradition of my colleague Peter Alvaro, who got it from his advisor Joe Hellerstein. But they're also known as sequence diagrams or time diagrams or space-time diagrams, if you want to sound really cosmic, and many other names. Since at least the 1970s, people have been using these diagrams for all of these decades in an attempt to wrap our heads around how concurrent and distributed systems work. In fact, I've been using them throughout this talk, and you might have even drawn one yourself on a whiteboard recently. These diagrams depict the events of interest in a system, often things like when and where a message is sent or received, and the causal relationships between those events across space and across time. And the way that these diagrams help us visualize executions of concurrent and distributed programs is so useful that we see these kinds of diagrams at all levels of academia and industry. But they are just pictures, not formal objects. And as my student Jonathan put it, in the worst case, you can barely manipulate them with a whiteboard eraser, much less with math. But what if they were formal objects? To reason formally about executions, we need a formal model of executions. And Lamport's own model from 1978 goes more or less like this. First, we have a collection of processes modeling a set of locations in the system. And next, every process will have a sequence consisting of the events that occur on it. Events can either be message sends or receives, or they can be internal events. And then we identify the pairs of events that comprise messages, where information propagates from one location to another. So here, for instance, on process P1, A1 would be an internal event on that process, A2 would be a message send event. This message is being sent to process P2, where A5 is the message receive event. So what you see here is a completely standard way to formalize executions, and it gets used all the time. But it does have some potential pitfalls. One issue is that it doesn't prevent you from representing something that's physically impossible, like a causal loop. So here's an execution that couldn't actually happen in a distributed system. To avoid accidentally writing down an execution like this, you would need to check your data or just assume that it's correct. The structure of the data itself doesn't really help you avoid this situation. This representation also doesn't stop us from representing inconsistent cuts. A consistent cut in an execution is something like this blue line with a happy face that we see here, where we're separating the events of the execution into a past and a future. The past is above the blue line, and the future is below it. If an event's on the past side of the line, then everything that's causally before that event also has to be on the past side of the line. That's what makes this blue line, in fact, a consistent cut. An inconsistent cut, like the one represented by the red line here, doesn't have that property. So in particular, look at the event A5. It's on the past side of the cut, it's above the line, but A5 represents the reception of a message that was sent at this event A2, which is on the future side of the line. So we know that a send is supposed to causally precede or receive, according to Lamport's happens before relation, but A2 is on the future side of the cut. So the traditional model doesn't help us avoid inconsistent cuts. If we just take a prefix of each of the events in this execution, like we've tried to do here with this red circle around each of these sequences of events, that's not going to be good enough. And the problem is that there's no connection between these processes that we're splitting into past and future and the messages that introduce causality constraints that we need to respect. And you might have heard of the software development dictum, make illegal states unrepresentable, which I've heard attributed to Yaron Minsky. Tell me if I have that wrong. Let's try to make illegal states unrepresentable in our formalization of execution. So what should we do instead of this? So to understand a little more deeply what's problematic about the traditional approach, let's take a closer look at it. Here's that same execution that we were looking at before. But I've turned the diagram on its side, I've removed the labels on events, but it's still the same execution as before, with the same structure. The only difference is that I've added these additional dotted gray and dashed blue lines to the diagram, which make the structure of the execution more explicit in the diagram. In this traditional approach, the top level structure is the collection of processes, P1, P2, P3. So the first thing we do here is visually separate the processes from each other with these dotted gray lines that are our spatial boundaries between processes. And next, within each process, each of the individual processes has a sequence of events in time, which are totally ordered. So we can make that explicit too by adding these dashed blue lines as temporal boundaries between the events. Unfortunately, we can't really do the same thing with messages, and that's almost by design. We decided to make the order of events within a process our top priority. And in this formalism, messages are a fundamentally different kind of entity. Notice, though, that these messages always seem to cross these gray dotted spatial boundaries that run horizontally instead of crossing the blue dashed temporal boundaries that run vertically. So those process local edges that cross the dashed blue temporal boundaries, those are inherently causally ordered by the structure of the data along each process. But the edges that cross the dotted spatial boundaries between the processes are not. And the fact that messages can leak this way across these spatial boundaries is what makes it possible to accidentally construct an inconsistent cut. This happened because we prioritized the spatial boundaries between processes over the temporal boundaries between events. What would happen if we transpose the order of decomposition? What if we lay down the temporal boundaries before we lay down the spatial ones? That is exactly what our approach does. So here's that same execution, but now it's represented as a causal separation diagram, which is what we call our approach. First, we'll lay down enough consistent cuts to separate every event. That's what these vertical dashed blue lines are. So instead of splitting up by processes first, now we're splitting up the execution by global time steps. And where by time, of course, I mean logical time. I've been calling these blue lines temporal boundaries, but I could have just as easily called them causal boundaries because potential causality follows the flow of time. So hence this name, causal separation diagrams. And then within each of these global time steps, now we can separate things out spatially. Now we can add the spatial boundaries between each distinct location. And we end up with this very different decomposition of our diagram, where the original decomposition gave us a structure consisting of 3 separated sequences of events. Now we have a single sequence, not of events, but of global steps. And in turn, these global steps are composed of local steps for each location in the system. In this particular diagram, for instance, there are 4 global steps arranged from left to right, separated by blue dashed lines. Oh. Each global step happens to contain 3 local steps, and those are delimited by the gray dotted lines. And something else that might jump out at you here is that some of the local steps don't contain an event at all. And of course, that's because our processes had different numbers of events to begin with. So separating out all of the events in one process will cause the events of another to appear more spread out. Another thing is that this decomposition isn't unique. It depends on how we choose our backbone of consistent cuts. For any distributed execution, there is a lattice of consistent cuts, and we're only picking out a particular totally ordered chain of cuts from that lattice. So we necessarily would get a different decomposition for every choice. But here's what's most interesting. Now, both messages and processes cross over the blue dashed boundaries, which are the causal boundaries. And as a consequence of that, if you have a diagram that can be decomposed this way, that diagram cannot contain causal loops. If a diagram of an execution can be constructed this way at all, we know that that execution has no causal loops. So we have that way to make illegal states unrepresentable that we wanted. Causal separation diagrams are built out of a small vocabulary of composable tiles. And here are all of the kinds of local steps that we can build up diagrams from. The first 2 should look familiar. A tick is just a local event on a process. A no-op is just the absence of an event. The last 2, swap and a sock here, don't model any actual events. Instead, they just allow us to kind of rearrange the wires through the diagram so that processes can communicate with more than just their immediate neighbors. And you can think of these 2 building blocks as being kind of akin to structural rules in a logic. And the middle 2, fork and join, are where the interesting stuff happens. These model the 2 halves of a traditional message being sent and received. But we don't call them send and receive. And unlike a traditional message, both the process and message state are coming out the right-hand side when we send, rather than having the message being diverted out the top or bottom. In fact, and this is the really weird thing about our model, it doesn't distinguish processes from messages at all. We refer to them uniformly as something called sites. This was my student Jonathan's innovation, and it took me a while to get my head around treating messages and processes as the same thing, but it actually makes sense to me now. A site is just a place where state can exist. A process sending a message is just a site, forking off a piece of its state out into the world as a new site. And a process receiving a message is just 2 sites joining together. So now, we can stick these tiles together in various ways and get CSDs. I've left it out here for brevity, but each one of these tiles also has a type, which says how we're allowed to compose it with other tiles. And I haven't shown them here, but we also have combinators for composing local steps into global steps, and for chaining global steps together into a full execution. And the type of each tile tells you how it can be composed with other tiles, vertically and horizontally. Okay, so what does all this have to do with interpreters, which are the topic of this talk? Well, earlier, when we were discussing what interpretation meant, I said that if we say that a syntax is interpretable, that usually means that the interpretation of an input is determined by the interpretations of its subcomponents. And to do that, we need to have a way to break down the input into its subcomponents and put it back together. This obvious way to break things down and put them back together is what we call an induction principle. And for the traditional formalization of executions that I showed first, we unfortunately don't have a nice induction principle. So for that representation on the left here, we just have a set of processes, we have a set of messages, and the structure of the data doesn't give us any guidance on how we're supposed to break things down and put them back together. So executions represented in that traditional way are not particularly amenable to interpretation, especially not if we want to work in, say, a mechanized proof assistant like ROC or AGDA or Lean that encourages inductive definitions of data structures. On the other hand, executions that are represented as CSDs come with a nice structural induction principle, since they're actually just lists of global steps. So to take a CSD apart, you can just peel off one global step at a time. And to put it together, you can just glue on one global step at a time. And this inductive structure is what makes CSDs amenable to interpretation. So CSDs give us a formal, graphical, and inductively defined syntax for representing concurrent executions. And it's something that we can then straightforwardly write interpreters for. So that's what we did. So in our OOPSLA 24 paper, we talk about 3 closely related ways to interpret CSDs. That is 3 ways of giving CSDs a semantics. The first one of these is an interpretation of CSDs into what we call causal paths. Causal paths are a proof-relevant analog of the classic Lamport happens before relation. That is, instead of simply asserting that 2 events in an execution are causally related, in a CSD, those assertions have to be accompanied by evidence of the causal relationship between events, and that evidence is just a path through the diagram. The next interpretation that we did is an interpretation into logical clock functions, which assign to every event some corresponding logical timestamp. There are lots of ways to do logical clocks, and this interpretation is parametric in your choice of logical clock implementation. So you can instantiate this same machinery over different logical clocks. And we did that for a bunch of clocks: Lamport clocks, vector clocks, a couple of different flavors of matrix clocks. And logical clocks like these are widely used in distributed systems to represent causal relationships. And the third way we give to interpret CSDs is into proofs that clocks respect causal paths. A logical clock that respects causal paths is one that satisfies Lamport's clock condition, which is just the thing that makes a logical clock a logical clock. So using CSDs, we're able to give a mechanized proof of the clock condition that is parametric in the choice of clock. Now, this isn't exactly news to hear that these clocks actually respect the clock condition. If they didn't, then they wouldn't be useful. But a lot of verification efforts, including my own in the past, just took this on faith. So there will just be an axiom somewhere that says that clocks preserve happens before relationships. Or if there is a proof, it'll be an ad hoc proof that's specific to a particular logical clock. Whereas this is a generic proof. And this interpretation-based approach to verification would have been really awkward and difficult if we didn't have an inductive data structure. But with CSDs, it just kind of fell out naturally. I want to wrap up talking about CSDs here by raising a research question that I have. So CSDs are a way to represent executions, but they're not great to program with. They have what I call the bookkeeping problem, which is that it can be tedious and verbose to construct a CSD term that has the right arrangement of tiles to be a legal CSD. A year ago, we tried writing a paper that turned CSDs into a parallel choreographic programming language. But every reviewer thought that it would be painful to program with, mainly because of this bookkeeping problem, and they weren't wrong. We took that to heart. We ended up taking a totally different tack for our parallel choreographic language. That's under submission right now. But my question is, do all inductive diagrams have something like the bookkeeping problem? Is that problem just inherent to working with inductively defined diagrams? And if so, are there places where it's been solved? And could those solutions apply to other inductive diagrams? Maybe we need better ways to represent these diagrams graphically that wouldn't require so much annoying bookkeeping. I don't have any answers here, just a couple of emails that I've exchanged with Harry Goldstein. But if you're interested in this question, then let's talk. So I'm at the end. To sum up, I've talked about 2 lines of work from my research group that turned out to be about interpreters all along. Library-level choreographic programming lets programmers write distributed programs as single, unified programs in their favorite language, and then dynamically project them to multiple endpoints. And causal separation diagrams are inductively defined data structures that are designed for elegant mechanized reasoning about happens before relationships in concurrent executions. But really, these two lines of work can be respectively summed up as, what if endpoint projection was an interpreter? And what if you could write interpreters for Lamport diagrams? So the takeaway that I have for you is, you can't go wrong by studying how interpreters and interpretation work. And then go study something else, apply your knowledge to that new domain, and reap the rewards. That's all I've got. Thank you.
Thank you for that lovely talk, Lindsay. We have time for questions. Please come up to the mic.
Hi, thank you very much for the talk. It was very interesting. When I see these causal separation diagrams, the first thing that I think is that they look like string diagrams for some kind of monoidal category. Have you tried to formalize them in that way, and if so, was it useful?
Yes, so the question is this actually a symmetric monoidal category? As a caveat, I'm not a category theorist in any way, shape, or form, but we think that CSDs are SMCs, but we have not really tried to formalize that yet. I've also exchanged some emails with Carlo and Julia about this. If somebody is interested in exploiting that connection, I think that could be really cool. My student Jonathan is also more of a category theorist than I am and observed this connection as well, but we haven't really taken advantage of it in any way. So I think it's a fantastic question, and thanks for bringing it up.
Thank you.
Hello, JJ, University of British Columbia. First off, really lovely keynote.
Thanks.
My reading group once read the Hastor paper and found it just a very beautiful system, but did kind of indeed struggled to reconcile that it's so beautiful and expressive and just a really nice way to work with that. There aren't really very many good properties as far as like asynchronicity and fault tolerance, and I think in the case of Hastor, also deadlock freedom, but it sounds like there's other stuff for that. I was wondering, for asynchronicity and fault tolerance, it's been like a couple of years since the Hastor paper. Is there any like particularly interesting work in this field or in this topic that you're excited about, I suppose? Right.
So so it's not just Haskell, it's the entire choreographic programming community that has traditionally been really bad about reasoning about fault tolerance. I think that is kind of indicative of the fact that a lot of choreographic programming people came from the concurrency theory community rather than from the distributed computing community, and it says something about what their priorities are. So I did try to acknowledge that elephant in the room. I think it's real. I think that choreographies, to be honest, are well suited for short-lived computations that run and then end, right? So something like an authentication, something like that. But a lot of folks who are working on choreographic programming are trying to push the boundaries of choreographic programming, do fancier and fancier things, do higher order choreographic programming, do location polymorphic choreographic programming, and so forth. And the fancier we get, I think the more vulnerable we are to faults. So maybe the role for choreographic programming in a larger distributed computing system ought to be more constrained, and then we can really leverage choreographic programming for the things that it's good at, and then use a different style of programming that expects faults more for the rest of our code. I don't have a great answer there other than that it's an issue. I will say though that so some folks in the choreographic programming community have been thinking about this. There's a paper on Archive called "Choreographies Meet Communication Failures," Fabrizio Montese and some of his colleagues have extended choreographic programming with something like promises or futures, right, which kind of decouple message sending and reception in a way that kind of enables some more asynchronicity and fault tolerance. But I think that also kind of, keeps the bathwater with the baby, right? Because we're kind of giving up on the thing that makes choreographies nice, right, to some extent. So I don't think this is a solved problem yet. Was there a second half of your question other than the fault tolerance?
There wasn't really a second
Okay.
half of my question, but I guess like a clarifying question. With throwing the baby out with the bathwater, do you think that there's anything that's fundamentally at odds with choreographic programming and fault tolerance, or is this just like an area that needs more work?
Well, yeah, so the question is there anything fundamentally at odds with choreographic programming? Well, maybe in the sense that the whole point of choreographic programming is to couple a message send with a receive, right? And the idea that a message might be lost seems fundamentally at odds with that, right? So, it does seem like there's a mismatch there. But maybe we can solve this, right? I haven't given up yet.
Okay, cool. Thank you very much.
Hello, Dimitri from IU here. I don't have this question super well formed, but I know in the sort of quantum computing world with CX calculus, which is a string diagram formalization of quantum computing, they have a notion of causality there defined, which feels very related to this. I don't remember exactly how they define it, but I think it may end up being isomorphic or equivalent or something to this. I'm just wondering if you've looked into that at all or any thoughts about that.
Sure. So I've spent some time talking with the physics people who built this framework on top of the ZX calculus. And so there does seem to be something really analogous between what they did and what we did. I'm not sure about their notion of causality. So I'm not a quantum computing person, I really couldn't say. But some of the questions I was asking about are inductive diagrams always vulnerable to this bookkeeping problem? Some of the issues that they had encountered reminded me of that as well. So I feel like there is an analogy here. I mean, like maybe this comes down to the first question where all of these things are actually just symmetric monoidal categories and we should solve it once and for all by looking at it from that angle. But somebody who's more of a category theorist than I am would have to be the one to do that.
Thank you.
Yeah, thank you for this super engaging talk. I was wondering, do you have like this a slide with this diagram compiled to CSDs? I would really love to see what that would look like.
Sure. So in our paper, I think this particular one is, so this diagram is a CSD, but there's also a textual representation of CSDs.
Oh,
so we can
okay.
represent this same CSD term in a graphical way or a textual way. In the textual way, it looks like it would look like fork, join, no op, et cetera, et cetera. And I think this literal diagram does appear in our OOPSLA paper. Also, I mentioned exchanging some emails with Harry Goldstein earlier, and he made a really cool tool that you can use to draw a CSD and then generate the textual description, which you can find online.
Okay.
So yes, that exists.
Cool. And then I was wondering about this EPP Haskell signature, and then you said that yes. And then, yeah, you have on the right-hand side, you have sort of quote-unquote semantics.
Yeah.
But since we're compiling syntax to syntax, isn't this exactly what a compiler is?
You got me. Yeah, so I did say that a compiler is a special case of an interpreter for the purposes of this talk. So,
Okay.
yeah, I mean, I guess it depends what you want to call a compiler. It's a compiler that runs at runtime, though, so.
Thank you.
Let's thank Lindsay again for that excellent
Thank
talk.
you.
We have a breakout in the lobby. If you are in the next session, please come up and check that your presentation will work and talk to Ben, who will be your session chair.
Oh, there we go. You can hear me? Okay. What's that? Oh, testing, testing, 1, 2, 3. Testing? Okay. I'll probably come. Let's probably just stand right here. Oh, I mean, I'll probably stand here, wherever I could see it. That's fine. Yeah. Okay, we've got the screen up. Hey, could you do me a favor and go like call people in one last time? Yes. So the session's starting right now. Yes, I will. Yeah, I'm gonna get started. Okay, I think it's about time to get started. We'll summon in the rest of the crowd from the hallway while I introduce our first speaker. So that's going to be Cohen, who's going to be talking about functional Perl, the first of 2 functional Perls in this session, on quick checking convergence of rewrite systems. And with that, take it away. This will be remote.
Thank you so much. Right, so this is a little project that I did both at Chalmers and at Epic Games. So suppose you are designing a programming language. An example of it is Verse that we are working on at Epic Games. And here is a part of the paper that we had where we gave semantics to this language using rewrite rules. So you have a pretty complicated rewriting system. And of course, you want to play around with it. So what we did was to implement this in Haskell, of course. So here's a little snippet of that. There's a term data type that captures the various features of the language, variables and constants and tuples and unification and things like that. And then we implemented the rewrite system from the paper as a function called step that takes one term and returns a possible list of possible rewrites of that term. So the rewrite rules, they may fire at any point in the term. So this is a non-deterministic rewriting system. Let's assume this rewriting system is terminating for simplicity's sake for this talk. And one question you may have when you give semantics to a language, is this rewriting system convergent? Or maybe you would say confluent. I use the word convergent. Convergent means confluent and terminating. So in other words, does every term in this language have a unique normal form? That's what we're after. And we want to figure out if this is the case and find counterexamples if this is not the case. We want to be very flexible with this. So you could implement all this in the theorem prover and try to prove these things, but that goes much slower. We want to do this development in Haskell, a programming language that has a fast experimentation support. So what do we want to do? We want to make a quick check property called prop convergence that says for all terms in this language, the term is this rewriting system is convergent. There's only one normal form that this term can rewrite to, and the topic of the talk is to fill in the dots. So what can we do with this property? We can test it by generating random data, and once we find a counterexample, we can then search for the locally smallest counterexample that we call, that's a process called shrinking, and this is a deterministic process. So we find counterexamples by random testing, and once we find a counterexample that is a term that may have 2 different normal forms, we shrink it to the smallest term in order to understand what's happening. Why does this term have 2 different normal forms? And testing that works by providing a function called arbitrary in quickcheck that generates a random term. And I'm not going to talk about this function at all in this talk, but shrinking works by giving a function that takes a term, which is a counterexample to a property, and then generates a bunch of smaller candidates to that counterexample over and over again until you find a locally smallest counterexample. And that's the topic of this talk, the shrinking function. So let's start by writing a very simple version of this property, this convergence property, by using this function norms that computes all the normal forms of a term. So it uses the step function here. It takes a term and it produces the list of all normal forms of this term. And there must be at least one normal form because we assumed that the rewrite system is terminating. So how does it work? We have this little local function called go, and it has a set of all the terms we've already seen. So we share the results of the already seen terms. And if a term cannot be rewritten anymore, then it's a normal form, and we keep going recursively until we find all the normal forms of a term. Now we can use this function in our first version of the convergence property, prop converges 1, by saying a term t, we compute all the normal forms of t. If there's at least 2 different normal forms, t1 and t2, then the property is false. Otherwise, the property is true. Now, this is a correct implementation of convergence, but it's very, very expensive to run. It's completely unpractical to run this term. Why is this the case? Because when we start with a term t and we start rewriting it, here's the cloud of all possible terms we can reach. The size of this cloud is exponential in the size of the term because there's many, many rewrites and they can all rewrite to each other and so forth and so forth. And there's many, many different ways of doing this. And even if there's only one normal form, the number of terms you can reach is exponentially large. And so running the property on a successful term takes too long time. So that's completely impractical. So I have to do better. So instead of computing all normal forms, then the next idea is to compute not all normal forms, but one arbitrary normal form. And I use this quick set generator to do that. It's called arbnorm. Given a term, it generates an arbitrary normal form by, at every point, if there's more than one choice to rewrite it, it picks a random choice here, and it keeps going until there's no more choice to rewrite it, and then we know that we have found a normal form. So we can use this generator to make a new next version of our convergence, which is very cheap. So what does it do? It says for all terms t0, I compute one arbitrary normal form called t1, and I compute another arbitrary normal form t2, and t1 and t2 better be the same. If they're not, then we find a counterexample. So this is very cheap to run. It goes very fast. We need to run more tests to find bugs, but the tests are very cheap to run, so it's a win situation. And we are pretty happy with the bug finding capability of this property. So we don't need to improve that anymore. But one really bad thing is that shrinking doesn't work at all. So we find bugs and the terms are very large and they look very random, and we can't make them smaller in order to understand the bugs. So this is no good feedback. So back to the drawing board. So but what's going on? We generate the term t0, and then we generate the term t1 and t2. But when we shrink t0, but then t1 depends on t0. And so we can't shrink this. So whenever we shrink t0, we probably won't find a counterexample anymore, and the shrinking is blocked there. So instead, we generate all 3 terms at once, the term we start with and the 2 normal forms. And we make this little helper type called fork, and we have this generator for fork. So we generate an arbitrary term t0 and 2 normal forms of it, t1 and t2, and we return all 3 at once. Why do we do this? In order to help the shrinking. So the property is now for any fork, t1 and t2 must be the same. But now when we shrink a fork, we can shrink a t0 to t0 prime. What should we shrink t1 and t2 to? Well, we can throw away t1 and t2 because they were normal forms of t0, not of t0 prime. Instead, we can just use our expensive norms function in order to compute normal forms for t1 and t2. And we can do it like this. So the shrinking uses the norms function. So we get fast testing. And once we find a counterexample, we get very, very, very slow shrinking. So sometimes you have to wait for hours to get an answer. But at least we don't find counterexamples so often. So this may be a good point in the design space. But it's still very annoying that the shrinking needs this very expensive norms function. So here's the idea that leads to the final idea of the functional Perl. If we have this function this term t0 and we normalize it randomly to 2 different terms t1 and t2, we can change this idea slightly by not randomly picking t1, but by having a deterministic normalization function that normalizes t0 to t1 prime and still randomly tries to find another normal form t2. So let's make this change. And this will not really, in practice, affect the probability of finding bugs. So we don't need to use randomness for both T1 and T2. We only need to use the randomness to find the other normal form T2. So we use this function for the green arrow is the function norm. It deterministically computes a normal form for the term by always pick the leftmost rewrite. So if there's no more rewrites, we have a normal form. Otherwise, we keep going. And we have a new helper type trace that is a trace of terms of rewrites to help with the shrinking. So, and we have this arbitrary way of this helper function to generate an arbitrary trace. Given a term, we randomly rewrite the term to a normal form and generate the trace. So we recursively do that every time we have a choice. We pick a random rewrite and we keep going until we have a normal form. So that's an arbitrary trace. And now we can go back to our fork helper function. So now a fork is not 3 terms. It's the term we start with and all the terms intermediately and also the term we end with. So the pink random rewrite is now called arb_fork. We start with an arbitrary term. We rewrite it arbitrarily, and that's the thing we return. And the properties now says for any arbitrary trace, normalizing the head deterministically should also be the last element of the trace. So pictorially, we start with T0, generate a random pink trace to T2. Normalizing T0 better end up in the same as T2. So T1 should be equal to T2. But what if we have a counterexample? How can we shrink it? Suppose T1 is not equal to T2. How does it help having this pink trace? Well, let's pick a point in the middle. T0 goes to T3, and then it goes to T2. And now we normalize T3, so we get T3 prime. Now one of 2 things can happen. Since we know that T1 and T2 are different, either T1 cannot be equal to T3 prime. So these 2 must be different. Or these 2 must be different. They cannot be all equal to each other because we have a counterexample. So now if these 2 are different, we can shrink to a new counterexample here. And if these 2 are different, we can shrink to a new counterexample here. And so we don't have to do any search or any expensive functions. So if T3 prime is not equal to T2, this is our new counterexample. And if T1 is not equal to T3 prime, then this is almost our new counterexample. We just have to normalize the end here as well to get to the final thing. So how do we do that? We change our property to not only normalize the head of the trace, but also normalize the tail of the trace. So now we say for any random trace starting in T0, ending in T2, we normalize the head of it, it must be equal to the normalizing the tail of it, or the last element of it. So the final thing that's left to do is how do we shrink a trace that only has 1 step? But now it's easy because we can just shrink the term T0 by itself, get a T0 prime, and look at all the possible steps we can take from there. But that's not expensive anymore. So here's the final shrinking function. If there's only 1 step in the trace, we just use the step function. And there's multiple steps in the trace. We pick an element in the middle, and we chop the trace into 2 bits, and one of them must be a counterexample. So we implemented this and evaluated it on a bunch of different examples from group theory, but also the buggy versions of the verse calculus, buggy versions of the SRL calculus. This is programming languages. We also found a buggy version of autosubst used in Rock, not made by ourselves, where we tried this out. And we also use this to find bugs in distributed systems implemented in an Erlang style. So it works not only for term rewriting systems, but also for general rewriting systems. And what we found was that prop converges 2, 3, and 4 is the fastest as finding bugs. So finding 2 random normal forms is good. And prop converges 4 is the fastest as shrinking, much faster than any of our alternatives. If you want to know more about this, read the paper. And that is the end of my talk. Any questions?
All right, we have time for questions. If anyone has any questions, please come on down to these microphones. Okay, we have someone heading on down right now.
Yeah, thanks. This was really cool. You said it took hours to shrink with, I think, prop convergence 3. Wall clock
In some
time.
cases, yeah. Yeah.
Yeah, okay. And how was the wall clock time for shrinking with the final solution?
I mean, not more than a minute, it's seconds.
Okay,
The
cool.
shrinking steps go really fast. Because there's no search happening here. All the shrinking candidates are generated very fast. And you can see that once you shrink the trace, there's only 2 shrinking candidates.
Yeah,
Yeah.
thanks.
So, Koen, you said at the beginning, we'll assume that the system is terminating. I
Yes.
imagine that verse, for example, isn't. And I'm sure you have a trick for dealing with that.
Yes, very good comment. So if you do this for general programming languages, we can't expect these to terminate, of course. So what we do in the verse calculus is there's one rule that unfolds recursion. And we switch off that rule when we do any of this kind of testing. And if we switch off recursion, then everything terminates. With a caveat, because the random testing could actually invent the Y combinator, and then you may not terminate anyway. And I decided to leave that possibility in just to make things exciting. And it's never found the Y combinator by itself. So.
Okay, we have a question from Discord. I'll read it. It says, naively, one would expect that if you shrink the source T to T prime, it should be possible to replicate the shrinking choice to a reduction trace out of T, possibly cutting the trace at some point, where removed parts were involved. I wonder if it is easier to play with this with a big steps presentation than a small step presentation. Intuitively, big step derivations are closer to normal derivations and have less irrelevant permutations.
Okay, so big step doesn't really work here, right? Because you need to have 2 big steps to different results. So big step is usually, I mean, maybe the big step is implemented in a non-deterministic way, and then testing a non-deterministic thing is just as hard as this. So big step by itself doesn't solve the problem. So you may, if you do shrinking, you may sort of keep track of what you've shrunk and reuse all the rewrite steps in the parts that you didn't shrink. But ultimately, these are affecting each other. And this is a general method where you don't need to know anything. This works for any step function. So that generality is worth a lot.
That makes sense. We have time for one more quick question, if there are any. Oh, I have one more.
It was it was a nice talk. One question I have is that when you have the 2 random traces and you say that there's only one that is needed to be random, then can it be proved? It seems to hold intuitively, but I don't know whether that can be proved or that is proven in the paper.
So in the paper, I actually mentioned that in the worst case, I say it's similar probability, but in the worst case, it's twice as bad. In practice, I mean, there's special cases where the probability of finding a bug here is twice as bad as probability when you use randomness for both. But in practice, that doesn't happen. I've done experiments and it doesn't make any difference. But you can create silly cases where if you do normalized rewriting, it's really bad. So you need to do randomness to find any interesting thing.
Fine, thank you.
Yeah.
The speaker one last time. So our next talk will also be remote. Patrick is going to be speaking about how to safely disregard unsafe behavior in compiler calculations. Oh, and looks like we're set up. So Patrick, I think you're good to go.
All right, thank you. Hello, ICFP. In this talk, I want to show you how you can ignore unsafe behavior when you do compiler correctness proofs. And in particular, I want to show this for the technique called compiler calculation. So let me tell you a bit about what I mean by that. So this is the setup we have. We have given a programming language here on the left, given by its syntax in the form of an algebraic data type. It's a simple arithmetic expression language, and its semantics in the form of an interpreter that evaluates the expression to an integer. And we want to derive from this setup a compiler for this language in some systematic fashion. But not only that, we also want to have some proof of its correctness, that it satisfies the specification. So if we evaluate the expression, we get the same result as if we would first compile it to some target code and then execute it on a machine. And so the way that compiler calculation achieves this is by actually starting to prove this compiler specification before we even have the compiler, right? And doing so in an equational style. And so as you do the proof, the definition of the compiler will become apparent. So you figure out what the compiler needs to be in order for the proof to go through, in the same way that you figure out what the value of x needs to be when you solve an equation. And so this also scales for more interesting languages. So if you have some more interesting stuff here in our expression language, where you might need a monad M here to represent some effects that your language might have, and instead of an equality down here, you have some form of bisimilarity that captures these kind of effects that say that both sides of this needs to have the same kind of behavior. But typically, this kind of equality or bisimilarity would be too strong of a requirement for a practical compiler. So what you typically have is something like this, for example, in ComCert, where you say you have a source program P, and you compile it to comp-P. And so what you require is that any behavior that the source program exhibits, any B, you must also find in the produced code. So, but importantly, you only quantify over safe behavior. So you don't care about unsafe behavior. So the compiler can perform some optimizations in these cases. And so the goal for this talk is to follow the same idea. So we restrict ourselves to safe behavior and restrict the notion of bisimilarity. So what do we mean by unsafe behaviors? So here's an example to illustrate this, and also to illustrate why this might be too strict to include them. So here we have a language that not only has integers, but also might evaluate to Booleans. So we have an if-then-else expression. We might be able to print an expression, the value of an expression. And so if we evaluate this expression language, we also have some effects captured by this monad M. And if we now evaluate an addition down here, right? So this happens in this monad. So we monadically evaluate X, and then we do a pattern match here. And this is a partial pattern match. So we pattern match this against the case that the result is a number. This is sort of a shorthand for what I've written here on the right. So I first evaluate X and get a value V out, and then I do a pattern match against the case that it's a number. And if that's the case, then I proceed. And otherwise, I return this stuck expression, which sort of is some kind of operation in our monad to indicate failure, some form. And then we also assume that our monad has some kind of print effect down here that we use. So some effect, some operation that takes a value and then prints that value on the console, say. Okay, so now with this in place, we can ask the question, say, given this arithmetic expression, true plus print 1, what's the semantics of this? And down here we have also given the abstract syntax tree. And if we now feed this to our evaluator here on the left, right, it would need to evaluate the left-hand side of the addition, and that would correspond to this case here, and then do this partial pattern match, and it would fail, right? Because we get out of this here, we get a value true out, and this would fail, and so this expression would evaluate to stuck and then something else, which is in fact equivalent to just stuck. So this expression would immediately get stuck. That's the only sort of observable behavior we get out of this. Okay, let's put this to the side and let's have a look at what a reasonable compiler might produce for this expression. And I've given the code here on the right. And so let's walk through that code and how it might run on a stack machine. Right, so first we evaluate, we push the truth value on top of the stack, so it corresponds to evaluating the left-hand side of the add. Then we have the right-hand side, so we first push the value n on top of the stack. Then we print this instruction, and so this would look up on top of the stack that number and prints that to a console. And after that, the machine would try to add the topmost elements of the stack. And this is where it would get stuck, right? Try to add a number to a truth value. So the observable behavior here is that it first prints 1 and then gets stuck, right? Whereas on the left-hand side, the evaluation gets immediately stuck. So these two sides clearly have different observable behaviors. But in practice, you want to allow this case here, because this only happens, this discrepancy, if we have unsafe behavior, right? If the left-hand side were actually a number, this would be fine, right? And so the goal of this paper is to allow this kind of reasoning about this setup where we might have discrepancies between the source and the target language in the unsafe behavior. Right? So we have this setup that I've shown you before, but now instead of using strict bisimilarity, we have some restricted form of bisimilarity that only considers some form of safe behaviors. So it allows us to ignore unsafe behaviors that we might find in the source. And in order to enable this, I'm going to use, in particular, the choice tree monad that allows us to capture algebraic effects such as non-termination, non-determinism as well. Okay, so let's have a look at how this restricted bisimilarity relation looks like. We call this skew bisimilarity. And as I've said, so this works on these choice trees. And I won't go too much into the details of what choice trees are, but suffice it to say, we can do pure computation, so we can just return pure values in here. We can express non-determinism, we can express algebraic effects, and we can express non-termination with this co-inductive constructor later here. But the important bit about this is that such choice trees, they give rise to a label transition system like this. Right? Here's this sort of the entire label transition system definition. So you can think of choice trees as a convenient algebraic way of describing such label transition system that are very convenient for the setting of calculational proofs. And so since we have this label transition system, we immediately get the standard notion of bisimilarity, which I've here on the screen. So it's the largest relation that satisfies these two conditions. So the first one simply says that if I have a transition labeled L on the left, I must have a matching transition labeled L on the right to a bisimilar choice tree Q prime. And vice versa for the second condition. Now, what this restricted bisimilarity notion does, the skew bisimilarity, is it has this precondition that we only say this only needs to be the case if our P, if the left-hand side is locally safe. And locally safe means simply that there is no unsafe transition. There's no transition outgoing from P with a label that we deem unsafe. For example, the stuck transition that I've shown earlier. Right, so if I just show this as a diagram, these two conditions will look like this. So any transition on the left must be matched on the right, but only if P does not have unsafe transitions like this. And the same for the other one. There's always on the left this restriction. Okay, so now how does this help us? So this relation has a very nice algebraic properties. So it allows us to do equational reasoning. So it's a pre-order. It has congruence laws for all the monadic operations that we're interested in. It satisfies the monad laws. It has some nice algebraic properties for non-determinism. But importantly, it satisfies this law here, namely that whenever we have a choice tree that is locally unsafe, then it is skew bisimilar to any other choice tree. So we can essentially ignore it in our calculation. So in particular, we have that this stuck choice tree, which we used before, is skew bisimilar to any other choice tree, Q. And that we can use in our calculations. So in particular, if we come back to our example that I showed you earlier, right, where we on the left-hand side, we have our source language semantics, which gets stuck immediately. On the right-hand side, we have our code produced by the compiler, which first prints 1 and then gets stuck. They're not bisimilar, but they're skew bisimilar, right? Since we are on the left-hand side, we have this unsafe behavior in the form of the stuck. So now our compiler spec looks like this. So we require that if we evaluate an expression, get a value v, and then put that value v on top of the stack. Here use Haskell notation for putting the value v on top of the stack. That should be not bisimilar necessary, but skew bisimilar to first compiling to a code and then running it on a stack machine, starting with the stack S. And so now we can use this specification to actually do our proof of correctness, or actually to derive correct by construction compiler. And this would look something like this. And I won't go through the details of the calculation, but the idea is that you start on the left-hand side of the specification, that's this line over here, and then step by step manipulate the terms until you get to the right-hand side of the spec, where you can then read off the definition of the compiler for this particular case of add. But the important bit here for skew bisimilarity is that it allows us to ignore unsafe behavior. So I've highlighted here. So this is the partial pattern matching that I've shown earlier, right? Where you evaluate an expression and then you have to pattern match it against a number. And using this unsafe behavior law that I've shown you on the previous slide, we can simply ignore it. We can turn this partial pattern matching into a trivial pattern matching against this variable v, and then just continue our merry way with the induction hypothesis. So this allows us to ignore this unsafe behavior entirely. And so what we end up in this calculation is then not a complete correctness, right? It's not, both sides are not equal in all circumstances, but only if the left-hand side is safe, right? We get this partial compiler correctness with respect to skew bisimilarity. But we have this relation between strict bisimilarity and skew bisimilarity. So strict bisimilarity implies skew bisimilarity, but also the other way around, given that the left-hand side is safe. So given that P is safe and we have this skew bisimilarity, we also have the corresponding bisimilarity. And so we can use this to derive full compiler correctness for safe source programs. Right? So if, for example, if we have some type system that ensures that, we can say that if E type checks, then we have the full compiler correctness property with respect to bisimilarity. Okay, to wrap up, so I've shown you I've shown you a toy example basically on how to use this skew bisimilarity on a very simple language. But the paper also shows some more interesting example languages. So, for example, we apply this also to a functional reactive programming language with an interesting modal type system, and also an interesting operational semantics that supports it, and derive a stack machine compiler for it that is correct by construction. And we do something similar for a concurrent lambda calculus that uses channels to communicate between parallel threads. So that's one side, and then we also extend the skew bisimilarities ever so slightly with a partial order, so that we can order the results of choice trees, and this allows us to also apply the same technique to register machines. So instead of deriving stack machine compilers, we can also derive register machine compilers, and we applied this to the same concurrent lambda calculus here. And so this is shown in the paper, but we also have this all formalized in Acta, and you can find this in the supplementary material. And with that, I'm happy to take questions.
All right. If anyone has any questions, just step up to the mic.
Mic working? Okay, great. Really nice talk. I was curious if you could just say a little bit about skew bisimilarity beyond compiler calculation. So, I mean, like, if I wanted to take skew bisimilarity and incorporate it into, say, like a ComCert style effort, what might that look like, and what are the potential benefits? Could you say a few words?
Right. Yeah. So skew bisimilarity is specifically for this kind of equational proofs where you're going to derive a correct by construction compiler, right? So you're very sort of you make sure that both sides have otherwise the same behavior. This is not what you typically find in something like ComCert, where you rather do you do this behavior refinement, right, where you expect that all behaviors exhibited by the target program are also exhibited by the source program, right? You have this kind of refinement. I suppose you could do something similar like that. So I wouldn't probably not use the same kind of skew by similarity. Maybe something that takes this notion of behavior refinement and derives from that an equational theory. That would be probably would be more suited for something like COMSOT or a verified compiler situation, or maybe something like trace equivalence, right, where you still require that things preserve the behavior, but you're not interested in that they are exactly the same in all concurrent behaviors.
Okay, we have time for one more quick question if anyone has one. If not, let's thank Patrick. Thanks, Sam. Okay, so our next talk is going to be by Shuwei Yu from, well, Xinjiang. I won't even try. Take it away, Shuwei.
Okay. Hello, everyone. I'm Shiwei Wu from Shanghai Jiaotong University. Today, I'd like to introduce our work, which is built around the simple proof trick. The trick lets an implementation proof directly reuse the facts already established by the algorithm proof, instead of proving the same facts twice. Let me start with a method that the P array is built on, using insertion into a binary search tree as an example. What the client ultimately wants is the triple. The tree stored at the P0 representing a mapping M. And after the insertion, it represents M with key bound to V. To get there, the two-layer method first introduces a functional model as a bridge. It's a pure function on trees and defined in rock. That is the insertion function from Software Foundation. And with the model in hand, the single obligation splits into two independent ones: implementation correctness and algorithm correctness. On the left, the implementation correctness, which states how a concrete implementation implements an abstract algorithm. Here, for this example, it is an ordinary separation logic called triple. The C function turns the tree stored at P0 into the tree computed by insert. On the right, the algorithm correctness, which states that the algorithm itself is correct. Here, for this example, a plain lemma about the model if the input tree is a search tree representing M, and the result represents M updated at key. In the binary search tree example, we use the ordinary separation logic called triple to express implementation correctness. In the two-layered method, we could also use relational quadruplet to express implementation correctness, since implementation correctness is about the relation of two programs. And we use depth-first traversal example to show it. The quadruplet states that the DFS sum refines the abstract program DFS. The precondition relates the two initial states, and the post-condition relates the results. Here, the concrete accumulator to the abstract unvisited states. Algorithm correctness is represented as a unilateral triple on the abstract side. When the traversal completes, the visited set is exactly the set of vertices reachable from the source. And composing them give what the client actually wanted. Starting from an unvisited graph, DFS sum leaves the accumulator holding the sum of the values over precisely the vertex reached from U, and the abstract program has disappeared from the statement. With the two examples, we could find that the two-layer method brings us two main advantages. First, separation of concerns. The implementation proof never argues about the algorithm properties. Second, proof reuse. When the algorithm is proved once, this algorithm proof serves every implementation and which will refine it. However, we found such unsatisfiable situation when verifying a string match algorithm, the Knut-Morris Pratt algorithm. It will first compute a next array, which means each entry describes a prefix of the pattern, the length of the longest proper prefix that is also a suffix. Let me take an example to make its next array concrete. And we use ABABC, and for the prefix A, there is no non-empty proper prefix that is also a suffix, so next 0 is 0. And for AB, and the next 1 is also 0. And for ABA, the string A occurs at both ends, so next 2 is 1, and for ABAB, the longest match is AB, so the next 3 is 2. Finally, for the ABABC, no non-empty proper prefix is also a suffix. Notice the fallback here, the Q drops from 2 to 0. So the trace of Q over the whole run is 0, 0, 1, 2, 0, with the fallback taken exactly once at P equals to 4. Now let's put KMP under exactly the same method. On the left, the abstract program getNext operating on lists. It walks the pattern with 2 indices I and j, extending LNext 1 entry at a time and falling back through LNext on a mismatch. On the right, the C implementation doing the same thing on arrays with P and Q. The implementation correctness stays relationally. The C getNext refines the abstract one, with the arrays representing the lists and the Q tracking J. And the algorithm correctness, the abstract program returns is the prefix function of the pattern and has the same length. Prove the 2 obligations, compose them, and the functional correctness of the C code follows. The sharp question is what happens inside the proof. The refinement environment contains what implementation correctness should own. M matches the abstract length, P matches I, Q matches J, and the concrete arrays represents the abstract lists. But it contains no range fact about Q. The axes still require Q below M and Q minus 1 inside the constructed part of next. But the abstract algorithm proof already contains the bounds we need. Its prefix-suffix environment gives J its range from 0 to I, and the length of the constructed LNext is I. At the string rate, the outer guard adds I below the length of L string, so both I and J are valid indices. At the fallback load, the inner guard gives J greater than 0 together with J minus 1 below I, and I equals to the length of LNext. That places J minus 1 inside LNext. There are natural facts from prefix function correctness, and they are exactly the bounds the C proofs need. Adding those facts to the relational loop environment would make the C proof re-establish KMP reasoning, exactly the duplication the 2-layer method was supposed to remove. The key challenge is not to establish the bound, but to carry it across modular proof boundaries without sacrificing separation of concepts. Our proof techniques bridge the gap while preserving proof reuse. That gap suggests the following idea. Annotate the abstract program with assertions that fail exactly where the implementation would be unsafe. The algorithm proof, which we already need, shows that this assertion never fails. The implementation proof can then use the asserted facts as the matching program points. And note that what the assertion is a statement in the abstract program only. Nothing is added to the C program at runtime. To make this intuition sound, we need 2 ingredients. The first is an abstract semantics with explicit arrow, and the second is a relational judgment that can observe that arrow. Let me start with the first ingredient. A computation has a normal denotation, initial state, result, and the final state, and an arrow denotation listing the initial state from which it may fail. For a third P, a true P returns unit without changing the state, and a false P enters the arrow denotation. This differs from assume P. A false assumption removes a behavior, while a false assertion records an observable error. That explicit failure is what allows the relational logic to transform the fact. Once abstract failure is observable, we can look inside the judgment that relates to a concrete failure. We have already seen the second ingredient in action, the relational whole culture. Now let us look at inside of it. It relates the concrete program and the abstract program under a relational precondition with phi relating their return values and final states. We will meet two conditions. The first is the result simulation. For any execution of the C program, either the abstract program errors or there is a matching abstract execution satisfying phi, algorithm correctness later rules out that error alternative are valid inputs. The second is error simulation. If the C program errors from a related initial state, the abstract program must be able to error too. The direction matters, it is not the converse. Written out, it says from related initial states, a concrete error implies an abstract error, which means if the abstract program never errors, the concrete one cannot error either. That is why algorithm correctness will establish that the annotated abstract program is error-free on valid inputs, and therefore the related C program is safe. By choosing where to insert an assertion, we choose which environment writes a course. The assert rule formulates that one side step, an assertion marks a failure boundary. If R holds, execution continues unchanged and R becomes available. If R fails, the abstract program reports an error. So the continuation receives a precondition strength by R. The abstract side processes the assertion, while the concrete side does nothing. So once the abstract program is about to run assert R, the rest of the proof may simply assume R. Importantly, the implementation proof need not establish R. Nowhere is there a premise proving it. Failure remains visible as an abstract error, and the algorithm correctness proves that branch unreachable on valid inputs. So the responsibility stays separate. Algorithm correctness discharges the assertion, and the refinement receives and translates the fact. Back to KMP. The two loops are now side by side, and C is unchanged. Only the abstract program has the assertions. At each assertion row, the C simplified started. First, before the inner guard, we assert that J is below the string length through Q equals J. That gives Q below M and justifies string Q. Second, before the fallback, we assert that J is below the length of L next with the guard J greater than 0. Next, J minus 1 is safe. Third, the fallback changed J, so another assertion restores the string bound before the next compilation. It also covers the string Q read after the inner loop. If the loop runs 0 times, the first assertion supplies the fact. Otherwise, the third restores it. Thus, 3 assertions size transfer only 2 distinct bounds. And notice what never appears on C side. No prefix-suffix arguments, only its consequence. With every side handled this way, the 2 proof layers can now be recombined. So let us combine it. On the left, the implementation correctness, and the C refines the abstract program and relates their results. On the right, unary algorithm correctness and the vertical composition rules joins them through one abstract execution, then hides that witness. So the result is a theory about C alone, no concrete error, and every termination result represents the correct table. It's a partial correctness and it not claim termination. And the payoff is exactly the premise. Each bound is proven once on the right, and the reuse at every concrete axis on the left. That way, separation of concepts restores. Now back to DFS for the second payoff and for the one fact and still has to cross. We met DFS sum earlier. Here, DFS find follows the same traversal, but it may return immediately when it finds the target. and stop scaling edges when a recursive call succeeds. To concrete programs with the same traversal skeleton, different stopping behavior, naively that would need two abstract algorithms and a duplicated proof of the shared traversal. Instead, one abstract DFS models both. There is a program from the previous slide, and growing in two places, the recursive step is now wrapped in a non-deterministic choice so that one abstract program can stop in either way. The stop branch returns false, and the DFS find take it after finding the target. The continue branch recurses into an unvisited neighbor, or returns true when none remains. DFS sum always continues, and the DFS find continues until it finds the target. The choice is angelic for refinement. The prover selects an available abstract behavior matching the concrete control flow. Say again, no randomized or oracle. The unary algorithm correctness must still cover every permitted outcome, and that is the second addition, the assertion, which is exactly what the earlier exit turns out to need. And the earth rule is now something we hand-wrote for 2 case studies. It shipped inside the working C verifier. The verifier is QCP, a qualified C programming. It takes annotated C program as input and uses symbolic execution to generate verification conditions about safety and functional correctness. In QCP, the abstract algorithm is state relation monad computation. So the assert rule of this talk is literally one library lemma. We use it on 2 further C program, UnionFun and Cosaraggio SCC in 2 sets. Here is the result. And the abstract program is always about the size of C. It is the algorithm, not an encoding of it. And the refinement proof is where the work is, which is exactly why we care the algorithm facts do not have to be reproved inside it. An abstract program is more than an input-output specification. It can carry immediately environments into an implementation proof. The algorithm proof establishes the environment, and assertion exposes it at a legend point. Error simulation makes this sound, and refinement consumes the fact vertical composition hides the witness. For KMP, the separate index reasoning from memory and representing reasoning. For DFS, one non-deterministic travel supports both full traversal and early exit. So free has a precise meaning. The implementation layer does not prove the environment again. We still place the assertion, discharge it in algorithm correctness, and maintain the relational state corresponding. That is the proof trick I want to show today. And thank you for listening.
Okay, we have time for a couple questions. If you have a question, come up to the mic. You going up to the mic? No. Okay, I'll lead off with this. So this might be a silly question, but I'm not that familiar with this proof technique. But it seems sort of the strength of this 2-layer proof technique is sort of a nice separation of concerns. But I get the feeling that these assertions are, what do I want to say, forcing you to tangle the concerns of one layer into another one. Is that accurate? If that
yes.
makes sense? Okay,
Yes.
so you are losing a little bit, so that's not quite the clean separation of concerns you had before, right? Because now the proof concerns of one layer are sort of impacting another one.
Yes.
Right, okay. I mean, I suppose this is a sort of a hard question to answer, but how complicated are those assertions? I mean, how much does this sort of qualitatively do these sort of concerns of this layer percolate up to the next one?
In our practice, I think the assertion is about the pure facts which will necessary for the symbolic execution. That it needs to assume that the execution is safe. So the assertion are mostly about the properties that supports the symbolic execution.
Okay, I see. Are there any other questions?
Yeah, I had a question. It looks like the programs that you write at these 2 levels actually have to be quite similar to one another, right? And you, in fact, showed us an example where they didn't match well, and you sort of had to modify the specification in order to better match the code that you were actually trying to prove. Is that going to be true in general? Should I imagine that the abstract program really is actually a pretty close match algorithmically and structurally to the target program, and the main thing you're abstracting away is like details of the implementation, like memory allocation, which clearly you inserted in the implementation?
Okay, that's a good question. And we think if you write the abstract program really close to the concrete program, and the proof will be easier. But it's not our purpose. We want to write the abstract program as a textbook program, and we can use it into different implementations, and which may take some trouble. So we use a search to make it easier.
All right, let's thank our speaker one last time. Okay, so our next speaker is Ryan Gibb, who will be talking about package managers a la carte. I want to make sure I got the right one.
Hello. Hi. So I will be giving a talk on package managers a la carte, a formal model of dependency resolution. I'm Ryan Gibb. Some of my co-authors are here from various institutions and places. Yeah, so there are a lot of package managers out there. We began with language archive networks in the mid-90s for sharing source code. Then system package managers emerged to deploy software packages and dependencies on an operating system. Programming language package managers used similar ideas to manage code for their particular ecosystem. Windows arrived relatively late due to a tradition of, I think, shipping dependencies in your application bundle. Nix pioneered the functional deployment software model in the early 2000s, which has become more popular in recent years. Build systems can also resolve package dependencies, and there are more exotic domains for package management too, such as hardware description languages, infrastructure, clusters, config, and CI steps. We might not consider some of these as package managers traditionally, but they share all the same atoms underneath the hood. So there has been a Cambrian explosion of package managers over the past decade or two. You can count, if you look closely, 4 here for Python and 4 for JavaScript alone. But they all fundamentally have some commonality. They all declare packages and their dependencies. So this is a Debian control file with a mail client expressing a dependency on a mail transport agent, which can be provided by postfix or exim. This is a cargo toml file for an SVG to PDF library, which depends on an image library with a PNG feature, and then the image library enables a dependency when the PNG feature is activated. This is a OPAM file for a USB project that depends on 2 possible implementations of a lightweight threading library and system dependencies that change name depending on the operating system it's deployed on. So these are all DSLs for describing dependencies with different semantics. But they all resolve these dependencies to select versions of packages. So let's take A depending on B and C, where B depends on D1 and D2, C depends on D2 and D3. Resolution selects D2 as the shared solution for B and C's dependencies. And then, given this resolution, we will deploy this to some environment like a file system or an image or there's more exotic targets, but we do something with this resolution. So these are large, complicated systems with many design decisions that go into them, and we might wonder, how exactly do they differ? What do they have in common? How can we interoperate between them? So consider a machine learning binary on Debian. It has C, Rust, and OCaml in one static binary, which requires APT, cargo, and OPAM to work together. We have dynamic Python bindings, which requires pip or another Python package manager, that call a GPU driver that must match the kernel driver APT installs. If we want to be portable off Debian, then we require more system package managers too, like APK or DNF. And none of them talk to each other. This fragmentation blocks ecosystems from expressing dependencies on other ecosystems. It leaves system dependencies, like we showed for OPAM, implicit and unversioned. And it hides vulnerabilities in the full dependency graph. You don't always know everything that is going into your program. So these systems, at most, have ad hoc one-to-one interactions between each other. How could we get all these systems to communicate? A lingua franca for dependency expression. That's the problem we're going to talk about in this talk. So this is our problem, and the solution is an intermediate representation for dependency expression. So this is a narrow waist diagram, a bit like IP, or maybe LLVM will land better for this audience. But the idea is every ecosystem has their own dependency language solver and deployment system, and they don't share much. But if we can put something in the middle, it allows us to interoperate between these systems. So on the top, we have ecosystems which have different properties. The package calculus, which we'll define, is expressive enough to model all those properties. And then we can pass it off to various algorithms to solve, and then deploy the selection on some system. So it turns out there's a very surprisingly small core that's expressive enough to be this intermediate representation, the package calculus. So we define N as the set of package names, V is the set of package versions, the Cartesian product of N and V is the set of packages, where a package is a name version pair, and R as a subset of these possible packages, the real packages which exist. So a dependency we define as a relation from a package to a name and a set of versions. So we can write this with infix notation, which we read P depends on N Vs, which means package P depends on name N and any version in Vs, where Vs is a set of versions. So let's take names as the alphabet and V as the natural numbers. We can illustrate this with an example. As before, we have A depending on B and C with versions 1. This is the dependency relation expressing these dependencies. And we can illustrate this as a hypergraph, where A has an edge to B and C. And the reason why it's a hypergraph is because an edge can be to multiple nodes expressing choice. So here we have B depending on D greater than or equal to 1 and less than 3, which under the natural numbers collapses to 1 and 2, which we can diagram as such. Similarly, C can depend on D with versions 2 and 3. So taking the real packages as all the packages in this hypergraph diagram, a valid resolution for the A package is selecting A1, B1, C1, and then D2 as the commonality. So I've glossed over what exactly a resolution is, but we can define this formally. So given dependencies delta and a root in the real packages, a resolution is a subset of those real packages, which is valid if it includes the root. We have a closure over the dependencies. So for every package in the resolution, for every dependency of that package on a name and a set of versions, we select a compatible version that must be in the resolution too. And this applies transitively. And the third criterion is version uniqueness. We can only select one version of a package. So for every name and version in the resolution, if two packages have the same name, then they have to share the same version. It turns out that this is, in fact, an NP-complete problem. We can show the hardness from a reduction from SAT. And actually, a lot of package managers deal with this complexity by reducing to SAT. So Other algorithms do exist that can give you better error messages using conflict-driven clause learning, but yeah, this is how a lot of package managers actually work. So we've claimed that this core is expressive enough to model the weird and wonderful zoo of expressions that we glossed over in the introduction. So let's look at how it can actually do that. Conflicts are supported by these package managers. They're basically an anti-dependency, so projects that can't be co-installed. So instead of saying we require a package at this version, we say we require the absence of a package with these versions. So this is Debian syntax for package A conflicting with B with versions less than 3. We can illustrate this as a hypergraph. What we're doing is extending our core calculus to model the real functionality. Here, gamma represents the conflict label. We use this as the symbol of the calculus. So as gamma, the valid resolution is just selecting A. We can reduce this to the core. This is a complexity theory reduction, so a translation that preserves the semantics using a synthetic package. So the angle brackets here represent a synthetic package name that we name as the conflict set. So that's B with versions 1 and 2. We provide this synthetic package at 2 versions, versions 1 and version 0. The versions don't really matter, but what they give us is mutual exclusion. So A depends on version 1 of this synthetic package, the B's depend on version 0. So using the dependency closure and version uniqueness, we can express conflicts. And it's trivial for this extension, but other extensions are more complicated, but we can prove the correctness of this reduction by the soundness and the completeness, and the soundness is a construction of S gamma from S, and the completeness is a construction of S from S gamma. Okay, concurrent versions is another not uncommon functionality of package managers. It's supported by these ones. This exists to address the diamond dependency problem. So here we have A depending on B and C, as before, but instead of B and C depending on D2, B depends on D1 and C depends on D3. And due to version uniqueness, this has no valid resolution in the core. So some package managers remove the version uniqueness restriction, and they allow multiple versions to coexist in a single resolution. So Debian actually does this by hand. libSSL 1.1 and libSSL 3 are 2 different package names in a Debian repository, and this allows them to coexist, even though they're underneath the same package. Other ecosystems support this as a first-class property. So instead of this manual encoding, they have some semantics for when versions can coexist, which we model with granularity. So versions conflict when their granularity G is the same. So cargo's granularity is the major version of a semantic version. So we extract X from an XYZ. And this means that versions can coexist when they have different major versions, and when they have the same major version, they can't coexist. Cargo does this because the types should be incompatible anyway at a major version bump, because if you mix types between 2 different versions of a package, if A tries to use a type from D1 with D3, you'll get a strange type error. NPM has a granularity set to the identity function, so there's no restrictions on when versions can coexist. That's why node modules can get quite big. So here we have some cargo syntax expressing a running example with B depending on D versions 1 and 2, C on 2 and 3. We can illustrate this as a hypergraph of the extension, where the only 2 versions which can't coexist are D 2.0.0 and D 2.0.1. Because the granularity extracts the major version, D3 and D1 can all coexist. So B depends on D, and it selects 2.0.1 to satisfy its dependency, and C depends on D, and it selects 3.0.0 to satisfy its dependency. So there's 2 versions of D in the resolution, which is allowed under this granularity. How can we reduce this to the core? Well, we can take inspiration from Debian's manual encoding and push the granularity into the version name, into the package name. So here we have D3 as a package name, D2 as a package name, D1 as a package name. Then we do the same with A, B, and C. The dependencies were just as before. But how can we express a dependency from B to D, given that the core only allows us to express a dependency to one name? So we can use a synthetic package to do so. So this angle bracket B1.0.0D represents B1's selection of D's granularity. So we have it at versions 1 and 2. And then those packages depend on the versions of D that B depends on at that granularity. So here in the resolution, we can see that the second granularity is selected and 2.0.1 is selected. And similarly, C can depend on D across granularities with an intermediate synthetic package 2. Features are the third and final extension we're going to look at today, supported by a few package managers. These are optional functionality selected per dependency, and they may add additional dependencies of their own. OPAM approximates this by hand. So the OCaml option F lambda package encodes a compiler flag as a package name. Cargo supports this as a first-class property. So here we have B depending on D with features alpha and beta, C depending on D with feature beta, and whenever D has feature alpha activated, it adds a dependency on E, and whenever D has feature beta activated, it depends on a package F. As before, we can illustrate this extension as a hypergraph. We have A depending on B and C with the empty set, meaning no features, B on D with alpha and beta, C on D with beta, and then whenever, so D is provided with features alpha and beta together. This is what Cargo calls feature unification. We don't provide two instances of B, one with alpha, one with beta. We provide them together. And then whenever alpha is activated, it adds a dependency on E, and whenever beta is activated, it adds a dependency on F. So how can we reduce this to the core? A to B and C, there's nothing fancy going on there. D, how do we represent these features? Well, perhaps unsurprisingly, more synthetic packages. D alpha, as a synthetic package name, represents the feature alpha being enabled for package D. And then whenever B depends on D, it depends on these synthetic feature packages. And C depends on D with the B, the beta synthetic feature package. And then we can add these optional package dependencies that are activated by a feature by just hanging that dependency off these synthetic packages. So there are a lot more weird and wonderful semantics out there that we could talk about, but time is limited, so if you're interested, the paper goes into more detail. We believe the package calculus can be an intermediate representation for dependency expression and allow cross-ecosystem dependencies. So every reduction we've talked about is proven sound and complete in Lean 4. And if you're working on package management or interested in this, please come and talk to me. I'll be around today and, well, the rest of the week. Thank you.
One quick question, or two quick questions while the next speaker sets up. Yeah, go ahead.
Hello, hello. Really great talk, very interesting. Could you say more about the NP hardness? Is it possible to drop some constraints, especially uniqueness, and get easier problems so that your package manager is maybe more reliable?
Right, okay.
It always has been weird to me that you can't have multiple versions of the same package, even in Cargo with them, the major versions.
Right. So I think the types interacting is the restriction here. If you want to share a type between D1 and D3, that is not supported. So that's why there are restrictions. Section 3.3 of the paper goes into a bit more detail on Go's minimum version selection algorithm, This uses semantic versioning, so you can only express a minimum dependency. The maximum is implicit by the semantic version. So that removes the MP completeness, but then the incompatibility is a property of the dependee versioning itself, but incompatibility is fundamentally a property of the dependency. I can talk more about this, but basically if you remove the hardness here, you have to move it somewhere else. So
Okay, sounds like maybe it just is hard, so thank you.
Thanks.
Hi, Gershom here. Look forward to talking to you afterwards about package manager stuff. One quick observation is that the synthetic packages you add have a wonderful correspondence in the literature to the fact that these structures look a lot like event structures in terms of concurrency theory. And adding the synthetic package, what you're doing is you're saying every conflict is monocausal, in this case from a version constraint, and having conflicts be monocausal is the reduction in the literature from general event structures to prime event structures. And prime event structures beautifully are domains, although I don't know what to do with that fact. But let's talk about that later.
Okay, I'd love to talk. Thank you.
Okay. Thinker speaker one last time. And
Welcome, everyone, to the afternoon session on testing and verification. I guess, are we ready to go? Yes? Okay, great. So our first talk will be given by Alex on bimodels and bioorthogonality for abstract machines.
Thank you, Derek. Thank you all. It's a great pleasure to be in Indianapolis. I'm really sorry. This is a talk about denotational semantics. Every single time I have to apologize. It's also an advertisement, not of myself, nor of my PhD student, April Tune, with whom this is joint work. It's an advertisement for a proof method that is great and that you should be using. There we go. Okay, so my new tirade is against small step operational semantics. They're terrible, don't use them. Why? Small step operational semantics, they're a piece of syntax, you move it around, it's great, you can teach it to undergraduates. However, it's extremely hard to prove anything about them. You need logical relations, you need all sorts of big things. Andy Pitts has done a lot of seminal work in this area, and the papers are somewhat challenging to read, but very well written. But they're not compositional small step semantics. You have to have tricks. Compositionality means that the semantics of something is defined in part by the semantics of its components. So you need to get over this hurdle. The alternative that I am likely to suggest to you is denotational semantics. That requires a lot more mathematical stuff, so that's also quite difficult, and also does not connect what the program does in practice when you run it with what the mathematical semantics says. To do that, you need to prove this thing called adequacy. Usually looks like this. It says if a program has the same semantics as a normal form, then the program does reduce to the normal form. Oh, look, we brought back operational semantics. However, there's a third way. Abstract machines, right, where theoreticians and practitioners both meet and think they can both do something useful. Abstract machines are great because they're already the start of an implementation, but do they have a compositional story behind them? Can we do maths over them? And the answer in this talk is yes. So a lot of the stuff in this talk is known, just putting it together seems to be a bit unusual for some reason. So what am I going to talk about? I'm going to talk about abstract machines as your primary object of study, and you should be doing this. I'm going to talk about how to give them compositional semantics, and I'm going to talk about how to give them, to prove meta-theorems over abstract machines using what we call bioorthogonal logical relations. I'm probably not going to get through the whole talk if I speak so slowly, but I also don't want to confuse you, so please ask some questions afterwards. And I'm going to do all of this in a calculus called call by push value. Call by push value is great. You should be using it. Every denotational model we know factors through it, and it's a very nice little calculus that supports effects. And please, 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 if you have effects, if you're doing anything but dependent type theory, use it. You won't regret it. OK, so it supports effects. We're not going to have effects in this talk, though. So sorry, that's for the follow-up paper. OK, quick introduction to call by push value. The point of call by push value is to separate what's a value, something mathematical, like 5 or 27 or a list of 3 numbers, to what is an effect, to what is a computation. So computations are things that can have effects. They can interact with an environment. So in particular, unit is a value, a pair is a value in left or in right, or a thunk is a value. A thunk is a computation that you've frozen and made into a value. Computations, the basic one is return. That's what you do in a normal lambda calculus. You return a value. You've got a bind, which Paul Levy, who discovered this, writes as 2. So I'm going to keep doing that because I'm used to it. You've got lambda, which means pop from a stack. You've got mv, which means push v to the stack and then run m. And you've got force, which you can use to force a thunk, which is a frozen computation. So it inverts the thunking. And then what I'm going to do, well, this has a type system with values and computations separately. So if you have a computation that's of type C, of computation type C, you can thunk it and get a thunk of type C. If you've got a function, look, functions take values, but they become computations after they take a value. You can read this A arrow C as pop A. So there's a computation that will pop A and continue as C. And if you give it a V, if you push it, then it will pop it eventually. The thing here is that you also have stacks, right? So stacks are what you have, they're your continuations. They're the things that appear when you try to implement this kind of thing. And you can look at this machine here. So if you have an application M applied to V, what you're going to do, you're going to push V on the stack and continue with M. If you have a lambda, you look at your stack. If there's a V on top, you're going to pop that and substitute it in for X, the bound variable. Similarly, if you've got a return, you look at the stack. Oh, sorry. If you've got an M2XN, what you're going to do, you're going to take this continuation. This is what a real continuation is, something that takes a value and continues to something else. You're going to push that on the stack and continue evaluating M until it returns something. Might do some effects in the meantime. And then when it does all the stuff it's supposed to do and is ready to return, you're going to look at the stack. Hopefully, you're going to find a continuation, and you're going to install it. So stacks also have types. This is something that's not as well known as it should be. So a stack has a type. It transforms a computation type to another one. So for example, if this stack transforms a C to a D, and I'm going to use this funny lollipop arrow, if you push a V on it, it becomes a stack that takes a function to a D. Why? Because if you give this stack, if you cut it with a function, it knows what to give to this function. It can give it this V, which is a type A. And then it's going to continue as K, and so on and so forth. And therefore, pairs of computations and stacks also have types. So you have a computation of type C and a stack that takes you from C to D. If you combine them, you're going to get this pair, a machine, really, which is of type D. So this will exhibit behavior of type D. OK, so why am I telling you all this stuff? The reason is really that once you have this set up, you can start proving theorems using a method called bi-orthogonal logical relations. And you should all be using this method. How does this work? You start with what we call a pole. A pole is a set of machines that you like. Here's an example. I'd like this machine of this type, M and a continuation, such that there exists a terminal computation, so something I accept as the machine has finished, and I can reduce this machine to T with an empty stack. So this is a set of machines that are good, that terminate. Poles, no matter what they are, this is a particular one, but you can pick any one you like, as long as it has this one property. If something is in the pole and a machine steps to that something, then that something is also in the pole. So the sets of good machines must be inverse closed. If you take a step to a good machine, your original machine must also be recognized as good. OK, once you've got this set up, you can define logical relations. And your logical relations now take the entire abstract machine into account. So you define 4 logical relations, your good values, your good terminal computations, your good stacks, and your good computations. And this has a it's impossible to get wrong, right? There's nothing left to chance here. When is a value of some type good? You look at values of some type, there's only one thing it could be. It can be an in left or an in right, and its body needs to be good. When is a return, remember, a terminal computation, one that's finished, when is that good? Well, when the thing it returns is good. When is a function good? Well, if you give it a good value, it should return a good computation. So for anything good, if you substitute it, you get out something good. And now comes the interesting bit. Once you've defined all that, then the next 2 steps are completely fixed. When is a stack good? A stack is good if when you couple it with anything, you end up in this pole. So a stack is good if I give it a good computation, I run them together, I get a good outcome. When is a computation good? Well, if I have a good stack ending in any type, if I couple these 2 things together, they end up being good. That's why this is called bi-orthogonality, because you use this pole once and then twice. If you trace this down, you'll find out that every single one of these definitions ends up using things at smaller type. And that's why Agda is happy with it, if you try and type it into Agda. It took us a while to get it completely right, but once you see it, you can't unsee it. And then you prove a little fundamental lemma. You say, if I've got a good value, and I've got an environment that fills in all these things, the free variables, with good values, if I fill it in, the outcome is good. Rinse and repeat computations, 25-line proof of whatever the pole gives us. What does this pole give us? It identifies machines that end in a good terminating state. OK? The empty stack, when you finished, you hopefully have the empty stack. That's a good stack. Stick it in there. you get from this corollary that any machine terminates. Okay, that was just a warm-up. Any questions? No. Okay, good, I'm glad. So what did we do in this paper? We reproduced, essentially, if you've ever heard of it, the 1973 memo by Gordon Plotkin, where Gordon defined a denotational semantics for the simply typed lambda calculus and did logical relations over the semantics. This was logical relations over the syntax, but you can do it over the semantics as well. And we did it in a style that comes from, really has been dominated by Thorsten Altenkirch and Ambrosch Coppolzy, the so-called type theory and type theory. And we presented it this way. You can present it in set theory as well, but we did it this way so we could formalize it directly. What do? You give a type for everything in your calculus. Contexts, suppose you have a type for them. This is your type of contexts. Value types, computation types, values in a context of a certain type. Suppose you have all this stuff that you would do normally in type theory, and suppose you've got constructors for every single thing in your syntax. So for example, you have a return that takes a value of type A and gives you a computation of type FA in the same context. And you have some stuff about substitution. All this is irrelevant. It's completely fixed by substitution. You don't have to think about it. OK, what do you do after that? You need one more thing. Two more things, really. You take a relation between pairs of machines and continuation. So pairs of computations and continuation. So you mimic machines at the mathematical level. And you say, well, I want a relation that mimics whatever the abstract machine would do. So for example, if I've got M applied to V, this will step to V being pushed on K and M. You need this relation, and there's one final thing. This thing we call a resolution function. A resolution function gives you the magical properties of values. If you have a value of type A1 plus A2, remember, in call by push value, these things don't compute. They're ready. So you should be able to extract from this either an A1 or an A2. So when you look at a value of some type, it must be either in left or in right. So that's what this function gives you. And you need an equation. You need to know that it actually maps the right thing to the right thing. So in left of V, if you apply resolve, you'll get the V, the body, which is going to be in the first component. And that's actually just an equation that says, if you know what this is in category theory, it's just a retraction. It's a sectional retraction pair. OK, so once you have this set up, you can have two models immediately. The one made of syntax, you just throw your machine in this. Your contexts are your syntactic contexts. Your value types are your syntax. Also, all of that is syntax, and that's clearly one of these things. And there's another one, the set theoretic one, or type theoretic, depending on what you like as a person. So the set theoretic one, let's call it B set. What's that? Contexts are sets. That's why this is set 1. It's a bit bigger. Value types, they're also sets. Stack types, functions, stacks, functions. Computations, also functions, from gamma to C, and so on and so forth. And you get two models very, very quickly. It's just one page of filling in an AGDA record really easily. And then you play the whole story we did in syntax once more. And it's very, very close to the thing you did in syntax. So when is something of some type good? Well, either there exists something so that the resolution is that something, and that something is good in the first component, or the exact same thing in the second one. So you resolve V, it becomes, I'm an in right, and then you ask that the body of the in right is good. When is a computation, a terminal one, good? Well, when it's a return, and the body of the return is good. And then same thing again. The poles are the same thing as before, but instead of syntax, they contain semantics. And then you prove the fundamental lemma once and for all, but now everything is interpreted. So instead of being syntax, you have taken a map that says, well, if I have V and it's a term of type A in a context gamma, then I interpret it as something in this val family, or val set, if you're a set theorist at heart. And then you get the fundamental thing. OK, so what can you get from this? It turns out you can get a lot. You have one theorem, you change the pole, and you get 4 different theorems immediately, just from this one result. So suppose you take the syntactic model. And suppose your pole is that S reduces to, in many steps, return and the empty stack. 2 minutes. 2 minutes. I need at least another 30. OK, so you get canonicity. You get adequacy. If you do the similar thing for semantics, you can get CIU equivalence, which is a thing I don't have time to talk about. And you can also get something called internal full abstraction, which is that if you choose your pole right, you end up with a notion of equality. And this notion of equality, if your model is denotational enough, is actual mathematical equality. OK, but that's not what people do. Implementers don't like substitution because it uses a lot of memory, and you should never do substitution if you're writing implementation. People use environments, enclosures, and things like that. The second part of the paper shows that it turns out that these things also have denotational semantics. So you can have a value closure and a computation closure. What's that? It's a value or a computation and an environment, a map that tells you for each tree variable what is interpreted by. And you can play the exact same story again. I'm doing the thing I'm being made fun of usually, of skipping many slides. And then you can do logical relations over those closures. And it turns out that it works beautifully, just as it did in the previous two cases. Interesting thing here is that you can prove, I'm going to skip through all that, but what you can do is you can prove a simulation theorem without thinking about administrative radixes, about thinking about anything at all. What you do, you show that the CK machine is a model for the CEK machine. You set up a little pole, this one here, and then you get that if the CK machine computes a return, then the CEK machine computes a closure, which if you unfold this closure, it's exactly the same value as you would have gotten from the CK machine. So this is actually what we wanted to prove when we started this paper. We ended up doing all this other stuff. OK, conclusion. If you give stacks in an abstract machine a denotation, they look great, they work great. You get to prove the fundamental lemma once, which I'm sure if you're a PhD student makes your life a lot easier. You can vary the pole to get all sorts of different results. And because we didn't force any quality or soundness, you didn't see any of that in the paper. You need no quotients, no setoids. You can just do it in Agda as it is. It's a slick proof method. Use it. We're doing effects right now. We have like 3 different versions, and they're all great, and we don't know which one to pick. And you can also find the formalization on Zenodo. Thank you very much.
Questions? Actually, if the next speaker could come up and get their laptop ready, that'd be great.
A very quick question. You showed this for CEK. Does this also? And then if you want to abstract the CESK in the style of Matt Knight's abstract machines, does it also work at that level? I'm hoping the answer is yes.
The answer is yes. I don't want to give away too much.
Okay.
But there's something in the literature on effects called a co-model. A co-model is like an operating system kernel. You send it signals, effects, and it does something, and you don't know what it's done, but it's done something. It returns something back. If you work with co-models, that's your S. Okay. So the entire theory works out, and you can import everything Plotkin and Power did 20 years ago.
Okay, so can we look forward to a paper on that in the future, or do I have to go look that
in 6 to 8 months?
Okay.
But if you send me an email, I can keep you up to date.
All right.
Okay. So you had this resolve plus function.
Mm-hmm.
So that said, if I had a closed value of a sum type, you have to be able to tell if it's an in left and in right?
Yeah.
But that's one of the things I might actually use a logical relation to prove, right? Like if I have an equational theory for my pure terms, I might use the logical relation to prove that everything has a normal form. So does that mean I can't use this method to prove that kind of logical relation?
That problem only happens if you're not in call by push value. If you're in call
if
by push,
I'm in call by push value with complex values, I do have that problem.
well, don't have complex values then. What's wrong with you?
Fair enough.
Yeah. So keep your values. Actually, even with complex values, if your model is denotational enough, right? If you interpret the sum type by a coproduct, it's either left or right. There's nothing else. And that's the key. It's like you keep the effects away. We'll talk about this later.
All right, let's thank Alex again. Our next speaker is Guanan, who will tell us to let it be optimized.
Thanks. So good afternoon, everyone. My name is Guanan from Tufts. Oops.
If you want it.
I can just use that. Yeah. From Tufts University. I'm very happy to talk about functional per paper, let it be optimized. I will soon explain what that title really means. So the paper is about multi-stage programming, which promises us we can write high-level programs that can generate low-level efficient programs for us. And you may have seen different forms of multi-stage programming languages, for example, as an extension to OCaml, to Haskell. There are MetaOCaml, there are template Haskell, or staging can be also implemented as a library or framework embedded in existing languages, like the lightweight modular staging framework in Scala, Squid in Scala as well, and more recently, the Build-It framework in C++. So let's look at a very concrete example of staging. So the classical example of introducing staging is this power function to compute the number of x to the power of n. And the idea is that if we know the value of n ahead of time, we can generate a faster implementation of the power function, right? And you can see from the type signature, we have this code of int for the value of x and the return value of this power function, meaning that there are code fragments to be manipulated and constructed. And this power function is implemented as a recursive function. So we have a branch, and in the base case of the branch, we are supposed to return some number of value of 1, but here we need to return a code of int. So we're going to use this primitive lift, which is primitive function that we can promote a value from the current stage to the next stage, as you can see from the signature here. And for the else branch, we need to construct a code to perform multiplication. And here we're using this underline multiplication operator, which takes 2 code of int and give us another code of int. And you can think of that, that's a programmer way to provide annotation to indicate some computation should happen in the later stage. And to really specialize this power function, we're going to use this lambda, underline lambda function, or primitive, to provide a binding or variable representing some unknown value in the current stage, which will be known later. That is this variable y here. And we're specializing this power function given that n is equal to 4. And this underline lambda primitive, you can think of as a higher order abstract syntax. We can convert a first stage function to a second stage function. Okay? And the journey code is pretty much straightforward. So here we have y, and we just times y for 4 times. There is additional multiplication for 1 that's coming from the base case in the original definition of this power function. But this is not the only possible code we can generate. We can also slightly optimize that a bit by not generating this additional multiplication of 1, because that's the identity of multiplication. Or even we can do better by not generating 4 times of multiplication, but only using 2 multiplication. We can create a sharing using light binding and directly multiply y for twice and using that in the downstream computation. And then we have an even faster code. So if you may have wondered, how can we write an interpreter that runs the program defined in the top about this power function and evaluate the program and getting the code from the naive code to the optimized code, then this function operates for you. So in a high-level description, we explain how to build interpreters for such multi-stage languages with a particular focus about automatic let insertion, which I will explain in a moment, and also with a particular focus about semantics preserving optimizations to generate better code. And we also want to explain everything in a modular fashion. Okay? So let me firstly talk about what is let insertion. So consider we have this program, which is the first stage function application. So the function body constructs the second stage addition. As you can see here from the addition operation, there's an underline. That's a second stage addition. And the argument is the lifted number of 42. Okay? And the question is, what should the journey code look like? Of course, we can do a syntactic manipulation basically by splicing this argument 42 into the function body. Then we get 42 plus 42. That's perfectly fine for this particular case. But now consider what if the argument here is an effective term in the second stage, like a function call. And we don't know what it does. It could print something into your terminal or maybe transfer some money from your bank account, right? And then in this case, the syntactic manipulation and splices may not be the ideal result. We have duplicated the term of function f and also duplicated the side effects of function f. And more importantly, the journey program is not consistent with the behavior of the unstaged callback value evaluation of the program without any annotation. So that is supposed to be the reference implementation for staging. A better and more sane way of doing that will be we can insert a let binding for that and use light binding to create a sharing for this function. And in this way, we can preserve the sharing and the evaluation order. So what I want to do here is we want to provide automatically let insertion in our interpreter implementing such a staging semantics. Okay? So our starting point here is a very standard environment passing style interpreter with a closure. So here what I showed is a pretty much standard lambda call by value lambda calculus. We have the variable case that look up the environment. We have the lambda case that packs the closure, and application just extending the environment to continue the evaluation. But we also need to take care of additional staging construct. For example, here we have this E+2 case that corresponds to the surface syntax. We have this underlined addition in the syntax. We have additionally the lift operation and also the run operation that we can evaluate a code constructed at runtime. Okay, so because this ICFP and it's all about functional programming, so I want to start with some non-functional solution using mutable states. And I think it's probably the best way for us to see its functional alternative. So we have this environment passing interpreter, and it also uses or maintains a mutable list to construct those light binding under the hood. So it's accumulate light binding, but it has an internal representation of that. So here we have this ST block, which is a list of pairs, and the pair is the variable name for that binding and also the expression to be generated. And we have two interfaces to use this underlying representation ST block. One is the reflect, that is to insert a new expression and also give a fresh variable names to be used. And this reflect returns this fresh variable names as a code value for the downstream computation in the interpreter, so we can compose larger programs. There's also a reify function. I'm not showing the full definition here, but what it basically does is to delimit the scope of this ST block. It does some mutation over that to save the context, and eventually it assembles the whole let expression. So the interpreter will using those primitives to define the semantics basically for those staging construct. For example, for this E+2 operation, we are evaluating recursively for E1 and E2, but for both of them, we're expecting a code value from that. And here we have X1 and X2. Then we can construct again the larger addition using that, using reflect. And what reflect does is to add a new pair of X3 points to or maps to this E+ program fragment and returns this code variable for that. So let's use the same example we have seen for this application, and I'm showing the internal trace of how the interpreter calls those reflect and reify, as well as how they change the ST block as a list here. So the first call of reflect will be happening over this function application term, this F. So when we're reflecting that, we're adding this new item into ST block with a fresh variable x1. Okay? And later, when we're evaluating into the function body, we originally have x plus x. But now, because we have the argument already that's becoming x1, then we're going to reflect x1 plus x1. Now this x1 plus x1 referring to something previously appended in the ST block. And finally, there will be a reify call that traverses this list of ST block, basically by folding that and constructing the whole let expression for us. Okay? So this is, you can see this very much imperative in nature. And the question is, how can we eliminate the use of mutable state here? Of course, we can do a state monad, but just threading this ST block and passing it around. But that doesn't really tell us so much about how let insertion works. So the question here, or to notice something here is, when we're reflecting something with a variable and expression, we don't really construct the whole let expression. We only know its variable and the right-hand side expression. We don't know the body yet. So the question is, who actually construct the body of that expression? It's happening something later in the interpreter, and asking this question, we realize that there's a missing continuation happening there. So let's do a continuation passing style transformation to make that explicit. So after doing that, we have this reflector function, which takes additionally a continuation. And this continuation does is to construct the body part of the let expression. So we get the body here, and then we can use the body to compose the whole let expression. Okay? So far, so good. But wait a moment, is that K continuation truly a continuation, right? If we look at it, we realize there are something to be finished after this continuation call returns here. So it's not really an undelimited continuation, but rather a delimited continuation. So we call that a meta-continuation, which suggests that we can do another pass of CPS transformation for the interpreter construction, and we can get a 2 CPS implementation of the interpreter. And now this reflective function takes 2 continuations, the K here and the kappa. And the K is the ordinary continuation that constructs the body of the let and also takes its own meta-continuation. And there's an outer meta-continuation, the gamma, that receives the complete let expression and forwarded outside. Okay? So far that's all good. But you may wonder why this is a preferred something we would prefer here. So obviously it also eliminates the use of mutable states, so that's good. But there are also some non-obvious benefits. For example, this implementation is a stack-safe implementation with tail call optimization. So all those control, there are tail positions, they are made explicit. So we won't worry about stack overflow when implementing that in a functional language. And also this style of interpreter becomes definitional in the sense that it is independent of the host language evaluation strategy. So we can faithfully implement this call by value, let insertion staging semantics in a non-strict language like Haskell. And finally, it also makes optimization easier by making the scope of optimization explicit, which I'm going to talk about in a moment. But before that, I want to give a quick overview about the treatment about let insertion we have in the paper. So let insertion is fundamentally about control, and there are many different ways in the literature to do that. We already have seen using a mutable state, using one continuation, which is very much like a normal form transformation, and also using 2 continuations or extended CPS. There are also possible ways of using delimit control operators like shift and reset, which we showed in the paper. And in the paper, we also provide a CEK-like abstract machine to perform the same style of stage evaluation, which you can implement in first-order language where you don't have the benefits of lambdas. Okay? And in the paper, we continue the exploration of optimization on top of this 2 continuation structure, and which I'm going to talk about those optimizations. So we want to optimize the code on the fly and directly generate a better code without really relying on post-hoc analysis or optimizations. There are also different ways to do that. One way is we can provide intentional analysis or basic code matching for the programmer so they can inspect the code fragments or AST and transform that. This is not necessarily semantics preserving. Or we can bake some optimization into the stage evaluation, and they're more like compiler optimizations, and they have to be semantics preserving because they're not really controlled by the programmer. So we're going to choose a second one. But also there is a subtle conflict between both. We cannot have both optimizations together, which will lead to a soundness issue. I won't go into details there, but in the paper, we do have a concrete construction to explain the conflict. Okay? So the first optimization I'm going to talk about here is the constant propagation. You may notice that a naive let insertion strategy will just inserting all those values, whatever they are primitive values, is not necessary. It's more preferred to generate compact code. We can directly inline those values into the places we're using that. This is very much straightforward in architecture by tweaking a little bit of the reflect function, because at the reflection time, we had a chance to inspect the expression to be generated. If it's already atomic value, then we don't have to go through the let insertion pipeline. We can directly inline that. Okay? We can do something further for constant folding. We can inspect the expression to be generated. If both operand of the plus is already a constant, then we can just compute that at compile time or staging time and directly returning the value. Eventually, we can generate code of a 3 instead of on the left here. And those continuation also makes scope-induced optimization more easy and straightforward. And the example here I want to talk about is dead code elimination. Suppose here we have a program, a function call, but the downstream code doesn't really use that, so it doesn't have to be generated. And to do that is to realize that when we're doing reflection, we can not only inspect the code to be reflected, but also we can inspect the code, the let body expression, hypothetically assuming that let insertion already happened. So doing that is a simple trick here for the reflection to after getting the body of the let expression, we can inspect that to see locally if it depends on this let insertion. If it's not, then we don't have to generate this let. We can establish its dead code according to a given dependency analysis. Otherwise, we just go through the normal let insertion by forwarding that to the meta continuation. So I won't have time to go through all the optimizations, but in the paper we discuss a bunch of them, like common subexpression elimination, algebraic simplification, function inlining with a-normal form renormalization, and also code motion, which moves let bindings across boundaries. All right, I'm up to time. So to summarize, in the paper we offered a distilled tutorial about building interpreters for multi-stage languages with automatic let insertion, semantics preserving optimizations in a modular fashion. So we discuss a bunch of techniques for let insertion and offer a collection of optimizations. So you can scan the QR code for artifacts. All right, thank you for attention. Happy to take questions.
Hi, could you explain how you made the optimizations modular?
So in the paper, we define those reflect as like a combinator, and we can compose those combinators. So each combinator only takes care of one optimization.
I see.
That's
so
roughly.
you just compose the optimizations for each combinator,
yes,
one after the other.
Yes.
Any more questions? If not, let's thank the speaker. All right, our next speaker is Oliver Flatt, who will tell us about animated pictures for slide presentations.
All right, very excited to be talking about slideshows today. Let's go and get started. So in this talk, I will first give a bit of motivation on why you might want to write your slides as code in a DSL. I'll then give you a taste of our DSL with how we make animations composable. We'll move on to more advanced features of the DSL, like replacing parts of animations after they've been constructed. And then we'll do a bit of reflection on what this might mean for DSL design in general. So let me ask everyone, what makes a good talk? Could it be a clear narrative throughout the talk? Nice visual examples, maybe? Bullet points? Lots of explanatory text, maybe covering the slide from top to bottom. A series of rhetorical questions could make a great talk. Maybe tasteful font choices. Sounds very important. But if you said yes to any of these, you'd be wrong. I say nope. None of these things matter. The only thing that really matters is fancy animations. I'm sorry, we can only watch that once. Don't have that much time. But yeah, there's more advantages to writing slides as code. We would want our animations to react to real data. Maybe you need to run your experiments last minute, the day before the talk. Be interactive. You can change this bar chart around live during the talk. Or be reusable and refactorable across different talks. And for all of these, we need to write some code. So, now that I've convinced you all that we need to write code for our slideshows, what tools should we use? Well, we could use PowerPoint, which technically supports Visual Basic programming, but the animation support is pretty limited. There's a lot to be said for Beamer, and a lot to be said about Beamer. But I'll just say that the animation support is very limited, and so you can get super fancy animations in a not incredibly painful way. You could go fancier and use HTML5 and JavaScript. There's a lot of nice websites out there, and I've seen slides made in this way. But you end up hand-rolling a lot of arbitrary JavaScript to write your animations, and there's not some sort of nice abstraction to use there. Going even fancier, professional YouTubers like Grant Sanderson have a library called Manim. This gives you pretty good animation support, but not one that's very composable. And so we've landed on Pict, which gives you fully composable animation support, and that's what this talk will be about. So having done a bit of motivation, let's talk about how the Pict DSL works and how it makes animations composable. For a warm-up, we'll do static pictures with the example of this fish here. And static picture DSLs have been around for a long time with the idea that you embed this DSL and have intermediate values be some sort of picture. Here's how we would draw this fish in the Pict DSL. We would call the ellipse function, which evaluates to what we call a pict as a value, and it draws on screen as an ellipse. We can call the triangle function likewise, and then rotate the triangle, giving us the tail of the fish. And then finally, we can compose these two pics with the overlay combinator and get the fish in the end. Great. So being in a host language of Rhombus, we would now like to do something a little fancier with our example and write a function at the host language to do something more interesting. Here is a function which puts any arbitrary pict in a fish tank. And we'll see in this example that it reads the width and height of the fish in order to properly size the tank. So putting this little red fish in, it'll read the width and height. And then it will overlay a rectangle of water in order to put the fish in a tank. And this works because the picture abstraction has built-in spatial information. It knows the width and the height. So if we put a larger fish that's green in the tank, we'll be able to measure the width and height of this now larger fish and get an appropriately large tank. After putting both fish in the tank, we can use the beside combinator to just put them next to each other. Great. So that's static pictures, and we can see how the host language helps us build up more complicated pictures. And now we'll talk about animations. So the first thing we might try for animations is to write animations as raw functions over time. And we'll see in this example where that starts to go wrong. So here is a red fish, and we're going to make it spin forwards and then backwards. And the way you could do that with raw functions is to make a function like this, spinny fish func, which takes the time t from 0 to 1 and rotates the fish over time. We could make the fish play forwards and backwards by branching on time t for after 1, it should play the fish animation backwards. And that looks something like this on the timeline. So, being functional programmers, we would now like to generalize this function to be reusable across our examples. And that means playing an arbitrary animation forwards and then backwards. So what might that look like? Well, we could take a new parameter, which is a function f, and then we could call f in each of the branches instead of calling spinny fish func. But there's a problem here immediately, and that is, what should we branch on for time? This is like an arbitrary host language closure, and we don't have any time information for how long this animation lasts. So like width and height, which stored spatial information, the solution here, and the solution we do in the Pict DSL, is to store time information built into the DSL itself. So here's what this animation looks like again, except in the Pict DSL. Here you can use the animate function, which builds up a Pict with time information. So you can specify here that spinning the fish forward should last 2 seconds. Then when we go to build our play then reverse function, it's generic over any Pict P, and we can switch between playing the animation forwards and then backwards. Taking our red fish, we can call play then reverse and see that it adapts correctly to the new duration of 2. If we ask Pict to explain this animation, you get a visualization like this. And this shows a timeline where the red dots are user inputs. So we're waiting for the user to advance the slide. Pict is built specifically for slideshows, and so baked into the time boxes is this user interaction. We call these spaces between user interaction and epoch, and we call the duration of those epochs the extent. And that's why we specified an extent of 2 earlier. So, moving on. Now that I've explained animated pics, the secret is that actually static pics are just a special case of animated pics. So if we took 2 blue fish and stacked them on top of each other, we would get something that looks like this. But we could also take our spinny fish from before and stack it on top of itself. And that gives you an animation that looks like this, where the spatial operator of stack is applied across time. Explaining this animation, we can see that the static version immediately fades out to the empty pict, and the animated one takes 2 seconds to play its animation before fading away. Great, so that was animated pictures and how they compose. Let's talk about more advanced and useful features like replacement. So to do this, I first need to build a sea urchin, of course. So I'll build a spike ring and overlay a circle on top of it. And this example will show how we can build up a row of fish, but after we've already built this pict, we can replace the blue fish with the sea urchin. So we're replacing the blue fish with the sea urchin, and we get a pict that looks like this. This replacement operator also works with user-defined functions. Let me show you how. So before we can take our tank function that we wrote that adapts to a pict and puts a tank around it, and we can put the red fish in a tank and replace it with the sea urchin. Now something interesting happens here, where the replacement does happen, but the sea urchin is poking out of the box. And that's because our tank function that we wrote before isn't adapting to the new picture. It was called onceAtTheHost language, and it grabbed the fish's width right here. And so to make the tank function adapt to the new picture, we need to provide pict with a little bit more help, and that comes as this asRebuildable macro here, where you specify the dependency on the pict p. And asRebuildable lets it replay that computation when you do the replacement, and now the box correctly adapts to the sea urchin. So this macro is pretty interesting. We're leveraging the host language to get more power out of pict here. And you'll notice it's a little different from the animation abstraction. The animation abstraction was built straight into the pict operators and values themselves, whereas rebuilding custom user new primitives needs to be some sort of macro, which then expands to something that looks like this, delaying the computation with a function and specifying the initial dependencies. And this is an interesting trade-off here between trying to bake it into the abstraction and giving the user control over when things rebuild and how replacement works. And so that's an interesting trade-off I'll talk a little bit more on later. Just to give you more examples of how to use the pict DSL, replacement works with animated pictures, of course. So we can take our spinning purple fish here, and we can take our row of fish and replace a blue one with a spinning fish to get an animated pict that looks like this. We can steal Keynote's magic move function and just make it a function at the host level. And the magic move, if you're not familiar with, it interpolates between two slides, giving you a nice transition. So in this case, we'll have two schools of fish, and magic move will automatically detect some sort of nice linear interpolation between these two picts, and it looks like this. Magic move is kind of cool because using picts facilities, you can actually write this as a user. So if you wanted some sort of crazy custom magic move, you could write that yourself, and it's not so many lines of code. Replace is also super neat for self-similar pictures. Here we build up a Sierpinski triangle of fish super easily. I think that one's pretty nice. And finally, this whole slideshow is an example of using our pict DSL, of course. And it's a particularly fancy example. One, because we made a one-off macro just for this slideshow. The macro is called evalSteps, and it takes a bit of Rhombus code and steps through it for you on a slide. So here we can see that our evalSteps over this fish example gives us a list of replacements that we can apply to step through the example. In this case, the list of replacements looks something like this, where the code for the ellipse is being replaced with what that code evaluates to, which is the rendered circle and so on. The triangle gets rendered next. Having this list of steps is super nice because then we can show the evaluation of this pict in a different way. Here's a big step evaluation of the same code where we grab the code that we want to evaluate next, fully evaluate it to a picture, and then plug it back into the expression. So we get our fish again in a different way. Great. Let's do a bit of reflection on Pict's design and how it might compare to other languages. One question you might ask, and we already saw this question come up in a previous talk on property-based testing, is PICT a shallow or deep embedded language? Just a refresher, a shallow embedded language is often described as some wrapper functions where the values of the DSL are directly values in the host language. So here in our arithmetic language, the subtraction would apply right away and give you 3, and then the addition would apply right away as well. In contrast, a deep embedding would do something like this, where you build up an AST first, and then you evaluate the AST using an interpreter written in the host language at the end. So we'll build up the addition and subtraction nodes, and then call a val at the end. So what does PICT do? Well, let's step through some evaluation to see. Here's our PICT in a tank. We build a rectangle, an ellipse, and a triangle. But when we rotate the triangle, remember that we need to be able to replay these computations to support replacement. So the rotated triangle has a dependency on the original triangle. Same for the red fish with dependencies on the ellipse and the rotated triangle. And the tank has dependencies on both of those. And so we see that we do have an AST here, so it's deep in that way. But where is our interpreter? I said that a deep embedding typically has an interpreter. Well, the interpreter is annotated on these nodes, right? Our box function was user written. The interpreter can't know about it ahead of time. It needs to react to new dependencies. And the user annotated that AST with that piece of the interpreter. And so we think this is a deeper embedding somewhere in between shallow and deep. This pattern comes up a lot in practice in a lot of super useful DSLs. And so if you want more examples, I'll refer you to the paper at that point. As a result, we can swap the tail here, and this interpreter will reevaluate the PICT with a purple tail. Great, so this was PICT. We encourage you to use it. And you might ask, what's next for this? Well, now that we have this, a nice thing we could add would be a GUI. That's something I would like, to be able to directly nudge things myself without having to write some code. And there's direct manipulation literature that might help us out here. You can also try using an AI to vibe code your slides. I used that for a couple of the animations in here. So I'm happy to take questions now, and if you want to try PICT, you can install Rhombus, which is shipped with the slideshow and PICT libraries. Thank you.
Thank you very much for doing this. I've been asking for a tool like this, once you had the GUI, for a long time. 2 quick questions. Can you publish the source code to the talk? And how long did it take you to actually prepare the code for this talk?
Right, yeah. I can make the source code available to the talk. That's no problem. It'll be in my talks repository. Took me about a month to make the talk. Some hand coding, a lot of messing with the macro. That was pretty fun. And then some vibe coding of some fancy animations. Yeah.
And you have animations over pictures, but can you animate things like time-varying values? Like fundamental numbers that I might then use within my pictures?
Yeah, I mean, you can escape and do anything you want, because like animate gives you a closure, and now you can do whatever in the host language. I'm not sure exactly what you're imagining. So, thank you.
First of all, thanks for a great talk. Unfortunately, I don't know if it's because of the fancy animations or the clear narrative, so we need more science done on that. So my main question is, what is the denotation of an animation? Maybe you're starting to answer that by saying it's a closure, maybe it's a function, and I'm hoping that I get an answer so that I can answer for myself questions like, what happens when I stack 2 animations that contain user policies?
Right, exactly. It can actually be a little hard to predict what happens when you stack pictures at first. But if you refer to the paper, we give you like the class for the PICT and its representation. And there are some reasonable defaults for spatial combinators like stack where it's applied across time. So it'll divide up all the epochs, align them in some way, and then apply that. So you can build intuition there. I hope that helps. Yeah, but I would refer to the paper. Thanks.
Thank you so much for the great talk. It really seems to be something like filling a market hole. One thing, maybe you have mentioned it, but what kind of files does this generate? And is there any limitation in what platforms it can be played on or something like that?
Right, well, so it's written in Rhombus. It's an embedded DSL in Rhombus. Rhombus runs in a lot of places. It doesn't quite run in the web yet. I think people are working on that, but it should work on most platforms. Does that help answer your question?
So basically, the slideshow itself that you use, is it a PDF or is it something else?
Oh, we use our own slideshow runner for this, like the animations, but you can also export to a PDF. You just won't get the live animations.
Okay,
Yeah.
thank you.
Hey, thank you. Nice talk. Chris Martins, Northeastern University. When I've tried to do things like this like use tools like this, and thinking of P5.js in the classroom, a thing that I've really wanted is a way to kind of adapt the design recipe philosophy to things like animations and even like interactive applications. And since you're working in Racket, I wonder if you've had any thoughts about that. How can people specify correct behavior and check that it's actually working correctly?
That's a great question. While making this presentation, we ran into all sorts of picked bugs, and the test suite is not super great. We usually test it by watching the slideshow ourselves. We'd love to go more in the direction of better testing things like how many epochs should an animation last. Snapshot testing can help with this because your old slides shouldn't break when you change things to the library. Or other properties such as like the width, relative width and positioning of things. I think there's a big maybe HCI testing crossover project to be done there now that we have a language instead of something else.
Yeah, I'd love to talk to you more about that. Thanks.
Yeah, sure.
Okay, we have 30 minutes for 5 presentations. We're going to allot 5 minutes for each presentation, and then we'll have a 1-minute transition time. We won't have any time for questions during this. If you want to talk to the students afterwards, that would be probably the best idea. So let's have the first presenter make their way up, and we will get going.
No. Yep. Sorry for everyone. Today I would like to present the ongoing project, which is tabular type for dynamic languages. Why? I'm sorry, because... No. Uh-huh. Yeah, I mean, I think they lost a lot of things.
Let's go to your display settings up here.
Yeah, and then
yep, go to just to the settings part.
settings.
Yep.
Yep.
Let's make sure you're on 1080p. And your space. Looks okay.
That's a.
Alex, it's also crop. Same problem.
What do you say? Oh, okay. Okay.
Okay, we're gonna shoot for 4 minutes, okay? I'm gonna give you a warning at 1.
Okay, okay. Okay, so today we'll be talking about some work we've had extending this like coverage type system. But first, to give some background, let's talk about property-based testing. So I'm sure we've seen it many times today, but at a high level, users provide some random input generator and some executable property, and then to test if that property holds, they can test that property on many of the inputs generated from the generator. However, if the generator doesn't actually cover all the inputs that we want, then even if the property holds on whatever it generates, we're not actually testing what we're looking for. And so we want some way of checking, do we actually generate all the inputs that we are looking for? And so some prior work developed this coverage type system, which it's essentially a refinement type system which helps us check this. So we have these standard refinement types which encode safety properties, but we also have these coverage types which instead enforce a minimum guarantee on the values that some expression generates. A useful way of thinking about it is with this diagram, where this orange circle represents all the values that some expression generates. A valid refinement type for that expression would be a superset of the values, an over-approximation, while the coverage type is going to, since it's enforcing a minimum guarantee, it's going to be a subset of the values. And we're enforcing that every value in the blue set is being generated. So if we go back to this sorted generator, we might want to give it this following type, which essentially is saying that all the members of we want to be able to generate all the lists whose members are between the low and the high bound. But because this only generates sorted values, we're not going to generate this list 3, 2, 1, since that's not sorted. And so it's not actually going to type check against this. However, there are maybe some properties that we test that don't actually care about the order of the elements. If we were to test all the different permutations, it would be a waste of time and additional complexity when just testing the sorted lists would suffice, depending on our property. And so we do want some way that captures this notion of set equivalence, where 2 lists are equivalent if the set of members that they have are the same. And we want some way of adding this notion of set equivalence into the type system, which right now, either you cover every element or it throws a type error. To handle this, we introduced this notion of quotient coverage types. And so in addition to the 2 types we saw earlier, we also introduced this new type which incorporates an equivalence relation. And instead of having to cover every single value that satisfies our predicate phi, we now say that at least one value within every equivalence class must be covered by this. And so this allows a much coarser grained notion of completeness than what coverage types have allowed previously. And to support this, we've also added this new subtyping rule, which if we look at the query that's issued to the SMT solver, the key challenge that we face is finding a witness for the existential. So I'll skip the algorithmic changes that we make to help facilitate this. But at a high level, or for results, we prototyped this new subtyping rule and it works, but we're trying to improve the performance and also make sure that our queries are decidable. We're also trying to extend this to cover some more complicated equivalences like alpha equivalence on lambda terms. And also we're trying to formalize the soundness of our algorithmic changes.
shoot for 4 minutes. I'm going to give you a warning at 1.
Okay. It's not. I think you should drag this wireframe to the screen, then like share from the screen.
Sorry? So
That, pull it back to this screen.
okay.
That works.
Can't see my pull it back. I can't see.
Yeah.
Oops.
Let me share. What?
Because okay, let me do that. Yeah. So So my associated mission is about the complexity of modern regex matching. So you probably know textbook regular expressions, which are described by this simple syntax. But modern regular expressions, like those found in JavaScript, Python, Perl, and Java, etc., are quite more complicated than that. They contain features such as capture groups, which can remember what was matched by a subregex, back references, which allowed you to match what was previously captured by a capture group, and lookarounds that allow you to stop matching at some point, match another regex, then resume matching at the original point. And my work consisted in clarifying the matching complexity of modern regexes. So for some background about known complexity results, textbook regex matching is done to be in P by NFA simulation, for instance. Modern regex matching, if you look it up on the internet, was widely thought to be NP complete, but the NP membership part is wrong. And the recent paper showed that regex matching with lookarounds and back references is p-space complete, but for custom semantics that does not correspond to most modern regex languages. So my work consisted in clarifying the complexity of real-world regex matching, and I showed using rock proofs that JavaScript regex matching in particular is p-space complete. So USATO's result extends to JavaScript. And as a bonus, I also showed that the lookaround-free fragment is OutP complete. So what do I need to? How did I do this? I needed a model in rock of a p-space complete problem. So the p-space complete problem that I chose is QBF, quantified Boolean formula. I also reduced QBF to JavaScript regex matching and formalized this in the reduction in rock. I gave a proof of p-space membership, also formalized in rock, by bounding the computation depth of a backtracking algorithm. And I used the mechanized semantics of JavaScript regexes, which is former work that was done in our lab, because JavaScript regexes are specified using more than 30 pages of pseudocode, which were mechanized in our lab, and then we provided more practical semantics that was proven equivalent to this mechanization. So the key concept to go from, so I will now focus on negation, which is needed to encode QBF. The key concept to go from SAT to QBF is negation, because for all x is equivalent to there does not exist x such as not. So the natural encoding in modern regexes to encode negation is negative lookarounds, which allow you to basically negate the results of regex matching. But it turns out that in modern regexes, it turns out that we do not need this negative lookaround construction to model negation for two reasons. In modern regexes, thanks to backtracking semantics, if you match A or B, you know that either A matched or that A didn't match and B matched. And in modern regexes, you also have atomic lookarounds, which means that if when matching look ahead A or B followed by C, if A matches and look ahead A, C fails, then you do not backtrack to try to match look ahead B then C. So as a conclusion, I gave the first complexity results for modern regex language against a realistic specification with mechanized reductions and bounds on computation depth, using a new construction without explicit negation and without Turing machines for proofs of membership. Thank you for listening.
Ivan, are you here? Yeah. Okay, you're on deck. 4 minutes. Okay. I'll give you a warning of 1.
Okay. Okay, let's see. Hallelujah. All right. Hi, everyone. Today, I would like to present the ongoing project, Tabular Type for Dynamic Languages. Dynamic language has become more and more popular in recent years because they are easy to use. To make it safer, people have tried to add type checking to these languages. Strict typing gives us the classic guarantees that well-typed programs do not go wrong. But the price is that it also rejects a lot of perfectly reasonable programs in dynamic languages. Permissive typing takes the other side. It only rejects the program when it is definitely wrong, so our flexible idiom will go through. For the program with undetected bug, the error will pop up at the runtime. So the tension between two directions leads to our question today. Is it possible to maintain the flexibility while ensuring some safety? And there are some existing answers. Gradual typing allows both static and dynamic typing existing one-type systems. But the static part is still being too strict, and the dynamic part is being unchecked. Another way is to make the type system more expressive to reject less programs that runs fine. But the type check could get expensive, type could be harder to read, and user need to write more annotations when writing the program. And all previous problem leads to our goal. To combine both typings, in addition to the safety guarantee, we also want to say that if a program is ill-typed, it must go wrong at runtime. We would like to incorporate both correctness and incorrectness reasoning to detect more ill-typed programs. Finally, we want a fine-grained mechanism to allow us to control the precision and complexity of type representation. First, type comes with modality in our system. Program with boxed modality means it will never crash. And program with diamond T means it either crash or evaluates to a value at type T. And program with diamond MT must crash at runtime, and such program we consider it as ill type. And here's the running example. Render takes V, depending on the Boolean flag, it either use V as a string or just return 200. We first try to give it a strict and safe type. Give it a string, it returns string or integer, and it will never crash. But in this case, application to an integer will get rejected, even though it is possible to return an integer at the runtime. So we make it permissive instead. Takes anything, return diamond, string, or integer. Now every calls go through. But the return type now says either return string or integer or crash, even though the application to a string will never get crashed. If we apply the function to an unknown input x, later on we use result y as string and x as integer, but notice that in order to use the result as string, in this case x must be a string, and the use case tells us something backward. And if there's a conflict in the program, we would like to reject it. So we would like to keep the collection of the behavior, while the box type gave us the static guarantee by accepting a subset of input and output. The diamond T recovers some information of what it is if it does not crash. By slicing the invalid input domain, we're collecting all the behavior of the program. So for the render, the return type gets 3 rows. Program either returns string, and in this case, V is string, or program will crash, and we know V is not a string. And for the type of a function, unlike implication, we read it as a conjunction as well. If a function application terminates, then the input is string and output is string. And looking back to the all previous example, they all pay out by the same tabular type. By matching the non-string row input, applying integer is now accepted with the outcome diamond integer. And similarly, we achieve the box type guarantee when applying the string. From the tabular type, we now have the info of x when using y. and we type check everything by joining all the types together, the information carried through the type will give us more refutation power. And to make the type simpler, we can merge the rows by sacrificing precision. And all the chain in this lattice allow us to type check at different paces, depending on the user input annotation or the type checking configuration. Thank you.
Pablo, are you here?
Do we have an adapter?
I do not know. What do you need?
A USB-C to HDMI. Thanks so much. 4 minutes? Okay, I'll keep a stopwatch on my end too. Hello, my name is Ivan Mladenov. I am an undergraduate at the University of Maryland, and I'm supervised by Leo and Alp. And everyone here has noticed that there has been a drought of property-based testing talks, so I'm coming with a bucket of water. Today I'll be talking about how we made QuickChick a little bit faster. So we'll start off with a quick example. Usually the way you'd interact with QuickChick is you'd open up Proof General or your favorite IDE, and you'll start writing some properties, and you want to test them. So let's say we have this max function that we've written, which just takes two natural numbers and then returns the maximum of both. And we can conjecture that this max function should be correct if we take two inputs, and for any two inputs, that the max return value will be greater than both. So as we step through, you'll finally get to the QuickChick command, and in a few seconds, you'll get some output in the output pane. And it feels kind of like magic. But if you've used any property-based testing frameworks before, like if you've done QuickCheck in Haskell or in OCaml, you'd know that they're written in the host language. So you'd think, okay, QuickChick is running in Rock, right? No, it did not. And there are two reasons that you can see just on this slide alone as to why that can't happen. The first one is in the output pane, which of course means you need I/O. And also, those 10,000 tests at the bottom were randomly generated. Both of these things cannot be expressed in Rock. So what's the solution that QuickChick uses? It relies on something called program extraction, which is basically just a framework in Rock that lets you extract Rock programs to OCaml, or Haskell or Scheme if you'd like. And so what this means for our property is that when we start with our property from before, anything that it touches, including natural numbers, which are provided by the Rock library, any of the QuickChick functions to actually run tests and use the generators, or any other external libraries that we use, have to also be extracted to OCaml. Then all of the dependencies that are used from these libraries get dumped to a single monolithic OCaml file, and then that gets compiled and run, and then reports the results back to you. And it works. So you might ask, who cares, right? It's perfect. But if you see the 3,000 line elephant in the room, there's a problem here. All of these functions that are being extracted, or at least most of them, are pretty frequently reused. You're always going to need your generators from QuickChick. You're always going to need a monad to represent the generator. You're probably going to need natural numbers, and QuickChick certainly will. So why don't we just take them out and have them somewhere else? And that's exactly what we've done. We've enriched the QuickChick library to use manual extraction, and we can point to already compiled commands, or sorry, already compiled definitions, like so. So if we have these inductive types, or if you have a function, or anything like that, we can say, okay, take these things, and anywhere you see them, instead of trying to recursively find them and then translate them to OCaml, just trust us and use these functions or type definitions instead. And that's what it does. So what does this mean for the new compilation process? It just means that we start with a property, and then you only need to extract a few key dependencies, such as running the actual test or any user-written code, and then that generates a much smaller OCaml file, which gets compiled and run, and then you link it against our library, and you get your results. Perfect.
We can also leverage OCaml just to get some extra performance boosts out of this. So for example, any functions that were poorly extracted or any compilation that was slower before is better now. We can use tail call optimizations on any of the functions that weren't tail called before. And then also just eliminating a lot of closures and any other optimizations led to a much bigger speed up in extraction because we're not walking as many functions and translating, faster compilation times because there's less to compile and it's already there, and then also testing from all the runtime benefits. How do we measure our results? We used Etna, which is a benchmarking platform for property-based testing, and it gives us some insight into how this affects the testing experience. So on large benchmarks like BST, RBT, and STLC, if you look at the smaller test cases, we see that the extraction time and the compilation time have shrunk and they're noticeable and it's a lot faster to run. But if you ever need to run a much larger benchmark, you can go down from something like a minute on the right side to under 10 seconds, which is super nice. And then the final upshot from this is that it's extensible. So if you ever see another function that hasn't been extracted yet that you want to extract, or something that could be faster in OCaml, you can do that and it'll be quicker in the future. Thank you.
Thank you.
Hi everybody, I'm Pablo Benario from University of Chile, and this work is also about property-based testing, and my advisor is Eric Tanter. So we have all written parts of our program that are incomplete, and we even have language support for this, which is weird because it's just a normal error, right? So a running example will be that we are implementing the multiplication function, and we start completely empty. Then we fill a little bit more and more. And what I'm trying to show here is just that order between programs where one is more complete than the other, which is called completion refinement. Okay? And we also like to test our code, right? So what happens when so in this case, we have a 4-unit case and 1 property-based case. So when we run this test, we naturally get the error at the 4th case. And what happens is that the whole is just a failure, right? And in property-based testing, it's even worse because you could have, if you happen to generate the first input hit the hole, you wouldn't be generating any more inputs in some frameworks, and it would just stop there, right? So the problem here basically is that we have one verdict for 2 different things, which is just incompleteness and hitting a real error, right? So what ends up happening is that the programmers just works around it by skipping the cases. In the case of unit test, you just skip it and you get it green again and nice. And in property-based testing, you could narrow the property and get it running again. So the problem with this is that you're basically breaking this link between tests and code, right? And you would have to fix it by hand. And if you have thousands of tests and you have skipped a lot of them, when you fill the code, you would have to be connecting them again by hand. So the idea here is to keep this connection and have a verdict of its own. So we would have incomplete, which is different than fail and pass. And this would be how the output would look. And in the case of property-based testing, this would be how the output would look. So this would allow for incremental development, right? So at the beginning, you would have everything yellow because nothing is completed, right? So if you have your properties written and you go and write or complete some of these holes, if you have an error, it would signal you, and if you have parts incompleted, it would not make a mistake by confusing both of them, right? So you could then have a mixture of even green, red, or yellow. And when you finally complete your code, would means that any input generated was successfully past the property or didn't hit a whole, right? So the important thing of this is that verdicts move only one way. If you have incomplete cases and you have a you have a failure, no matter how much you complete your code, you're gonna get, no matter how much you complete your code, you're not gonna fix the error, right? So this is based on basically what a property-based testing runner is doing is running this property where filter and check are user provided and could be incomplete, right? And in a recent paper in ICP, they developed this reformulation of the property where you could reformulate it to be incremental, which is monotonous with respect to completion refinement, right? So I actually implemented this in QCheck and Alcotest, so it was pretty simple. It's only like 40 lines of difference, and I'm pretty sure you could do this for every other framework. And I actually evaluated this at the OCaml compiler, multi-core test, and what I did was just making holes in the compiler, and what you expect to see is to just keep the test running and test the completed parts of the compiler, and the ones which are not, you would just get an error. The ones which are not, you would get incomplete. So that's it. Thank you.
We'd like to thank all the participants in the student research competition. We will present the awards to the students in the business meeting after the break. Thank you.
Hello all, I'm Robert Travers from Radboud University Nijmegen. I will be the General Chair of the next ICFP, which will take place in Nijmegen, the Netherlands. The PC Chair will be Steve Zadansvich from University of Pennsylvania, United States. The conference will take place from Hello all. Hello all, I'm Robert Travers from Radboud University Nijmegen. I will be the General Chair of the next ICFP, which will take place in Nijmegen, the Netherlands. The PC Chair will be Steve Zadansvich from University of Pennsylvania, United States. The conference will take place from 26 September
You should get someone to see about that. Your cough. Okay, you ready? Okay. Thank you, everyone. I hope everyone has been enjoying their time at ICFP. It is somewhat of a surreal experience for me to be standing up here talking to all of you. I think my first ICFP was 20 years ago when ICFP was in Portland, and I was a young PhD student, so it's been fantastic to get to give back to the community and to also bring this community here to Indiana University, and to have all of you, my community, here to celebrate functional programming together. So I want to talk a little bit about what we've done, how it has gone here. So ICFP this year has 213 attendees at last count, which is down something like a third from the previous attendance, related to many factors, but most significantly, I think, the difficulty of traveling to the United States for many people. We had, however, nonetheless a great program, 39 papers, 125 total talks, 11 co-located events, 3 keynotes, of which we've had 2, and both have been fantastic, and I'm really looking forward to Dan's tomorrow. So just to provide some information about the registration and who's attending, we had about 40% of registrants are students here, and which is something that ICFP values, and I think we've worked hard to bring a lot of students in. I see many student volunteer shirts here, and which is a particularly fun way to bring a lot of students and help them to be able to come to ICFP. A different demographic breakdown for in-person attendance. Of the 186 in-person registrations, almost 70% are from the United States, which is a significant change from the usual breakdown when it's normally closer to even between the United States, Europe, and then a small 15 to 20% from the rest of the world. So again, that's a big reason why registration is down this year. We also had 27 remote presentation registrations. So many of those people coming from Europe, but also from other parts of the world. Partly because of this, this has been a more hybrid ICFP than we have had in the past. 10 of the 39 ICFP talks themselves have been remote, and 29 total remote talks. The last number I got from the AV team was that we had up to 467 people watching the live stream yesterday, which is really great to see that we're reaching a very large number of people via the fantastic work that the AV team has done to make this accessible for everyone around the world. One question that people always have is, what are you spending all of this money on? ICFP is not cheap to register for, as I'm sure everyone sitting in this audience is aware. What are we spending that money on? So I just want to show a little bit about the budget here. So this first gives you a sense of scale for how much money it involves to put on a conference of this scale. We originally budgeted for approximately $450,000. Because of the lower attendance, our actual expenses are lower than that, primarily because we spend less money on coffee for people who aren't here. So in practice, this is what we ended up with. You can see the different expenses. The biggest one is catering, then the cost for this fantastic venue over this whole week, which includes the staff time of the IU events staff that have worked really hard to put this on. But then we have a significant amount of money that goes to the ACM, as that they charge every conference in return for their fiscal sponsorship of SIGPlan in general and this conference in particular. This is a large amount of money. On the other hand, this is what enables us to just run a conference and not have a bank account and not worry that if we go $500 over budget that I have to take up a collection plate to you all. So as you can see, we're ending up with probably a surplus, a very small surplus, because we budgeted for a significant contingency that ended up, and the contingency ended up being that we had significantly lower attendance. So this just should give a sense for the scale of what we're spending money on. And you can also see, where does the revenue come from to put on ICFP? Primarily, it's from registrations, but we do have $58,500 of sponsorship, which makes an very large difference in our ability to put on this great conference and sponsor the things like support for students that we value. I will thus take a moment to thank all of our sponsors who have contributed significantly to making this happen. So can we all have a round of applause for all of the sponsors of ICFP? I see many representatives of these companies sitting here. Thanks to you in particular for your continued commitment to this conference. I did want to mention that this year we had a sponsor who we considered, and then after receiving significant feedback from the community, we declined. I think we, the organizers of ICFP, appreciate everyone's feedback. I think this was resolved in the correct way. And we, the steering committee for ICFP, plan to take steps to vet sponsors to ensure the best interests of the conference going forward. So thank you to all the people who advocated for your views. And now is the most valuable time for me. So I've been telling lots of people this week that Being general chair, you don't actually do anything. You just get to ask people to do things. Mostly I do that over email. So I calculated today that over the last 2 years, I sent somewhere around 619 emails to different people to make this conference happen. And I received many more emails than that. But it's the people who I was sending those emails to who did all the work. And so I want to take a moment now to thank those people. So the first person who did the most to make this happen is our program chair, Manuel Serrano. Manuel put together a fantastic program, put together a great distinguished program committee, managed numerous tricky and unexpected aspects of it, scheduled a program that involved more time zones than he was expecting ahead of time. And as you've seen, ICFP has a fantastic program this year. So let's thank Manuel again. However, there's numerous other people who worked hard to make this conference happen. So this is the organizing committee. Every one of these people worked really hard. So Ben Greenman and Jiasi Shen are the workshop chairs. Workshops are part of the lifeblood of ICFP. Jules Jacobs is the web chair. I can't tell you how many times I emailed Jules to say, there's something wrong on the website, and 3 minutes later I got back an email that just said, done. Sam did the publicity, let all of you know that you should come and join us here at ICFP. One person who I particularly want to thank is someone I had never met before today, which is Nolan Royalty, who is going to tell you later this afternoon about the ICFP programming contest that he organized. Sun Ho and Lionel Perot managed the artifact evaluation process, which has now become a fundamental part of how we do publications. Kimball Germain and Alexandra Moine managed the student research competition, which you just saw several great talks, and we had posters last night, and we'll hear the results of that in a little bit. Alejandro Russo and Casey Sivaramanakrishnan are the ICFP diversity chairs, work hard to make this a welcoming event. Daniel Winograd Court, who I mentioned earlier, is the industry relations chair and raised tens of thousands of dollars and managed our relationship with sponsors to help make ICFP possible. Our fantastic AV team, and the AV chairs in particular, Eloise Christian, Angela, Alexander Bai, and One An, did a fantastic job to make the enormous amount of work that the AV involves happen. And finally, two people that I owe a lot to in making this happen, our two student volunteer chairs, Paulette Karankovich and Darshal Shetty. So please join me in thanking all of the fantastic people who made ICFP possible. And then I want to thank particularly the staff at both our SIGPlan event managers and the IU event staff who made this possible. Nuringa Young and Mariana Kuatara from Build Stuff, who managed registration, who did so many things that I didn't even know that I needed to have done. They had already done before I knew to ask about them. And so thank you. And then Kayla Reed and Nate Sparks from IU Event Services. Kayla is the event manager, and Nate, the AV person, who knew so much about how to run a conference that I didn't know before and probably still don't know, but they made it possible for this to happen here and helped me out every step of the way. So thank you very much. And then finally, thanks to all of you for coming to ICFP, bringing your best work to ICFP, bringing yourself to ICFP, and making this an incredible community that I've been honored to be a part of for the last 20 years. Thank you. So at this point, I want to take a couple minutes if people have questions or comments about the organization and functioning of ICFP of any kind. So this is just an opportunity to comment. We do not have time to have a long discussion about conference mechanics, but I want to give people an opportunity to make comments to the community.
I mean, I guess I can start. I think this is like pretty well known. I was pretty public about this, but I was really disappointed to see that Anduril was a sponsor of ICFP. I was happy that it was dropped, but I'm just wondering, like, where is the future for ICFP? Are we going to be taking money from people who are making missiles?
See, this is what you get, Paulette, for coming in late. We discussed this extensively as a steering committee. We're not planning to take sponsorship from Anduril in particular, and going forward, we're going to have more members of the organizing committee and the steering committee review future new sponsors to ensure that things benefit the ICFP community in the appropriate way.
Hi, I wondered, and it may be difficult to answer, whether it was cheaper to organize ICFP at a university than at a hotel or not.
So yes is the answer, both because IU Events charges less money for things overall than a typical hotel would, and also because we were able to get a significant discount on the prices because this is Indiana University where I am.
Hi, I just wanted to say it was really, I suppose, inspiring to look at the budget breakdown and kind of notice that, yeah, hotel and venue and catering costs have kind of decreased substantially, but also that the overall budget was, yeah, in the black. I suppose I just want to say that I appreciate that as a student, and particularly seeing that had there not been various contingencies with like people kind of staying in Europe and such, that the conference would have been substantially under budget. I guess I would just like to voice that this is great. It would rock if ICFP would continue to do this, and if this could kind of eventually lead to reduced prices overall, I suppose. But I mostly want to say, yeah, thank you all for the conference.
Hi. I would like to express my grievances with the diversity events for
for one, the women's dinner event did not have any women faculty showing up. I am pretty senior at this point. I am pretty integrated at this point. But I remember like my first ICFP, it was the only time I was able to speak with like some of the women senior faculty. It was like a very valuable time for me early on. And I feel bad that people this time around did not get that opportunity. Additionally, there were no signage at the LGBTQ lunch. So I believe like some people, people were really confused on where to go. I think like some people got mixed up and like showed up to their room. And I think we just need to do better. Thank you.
Can I just add a quick addendum about being cheaper at a university? I will say that even though it's cheaper than a university, logistically it's been kind of a nightmare because the AV team needs time in the evenings to set up and do trainings, and they have not had that time, so we've been extremely rushed or having to get up super early to do these things. So, you know, there is some benefits to being in a hotel for setup because you can basically be there at any point.
I would have one technical question. How do people usually volunteer as a student volunteer? And is it possible to do so if you are not local to the...
It is certainly possible to volunteer. Many of our student volunteers are not local, and I believe there's a call for student volunteers every year, and I anticipate there will be one again for ICFP 2027.
Okay, thank you.
Manuel? Okay, thank you everyone. And next, Manuel is going to talk about the program.
It will be simpler. Great, wonderful. So maybe first thing is that it seems to be the session where we thank each other, so I guess that we have to thank Sam for ICFP this year. So thank you, Sam. And on a personal note, I must say that it has been a pleasure working with you, and everything was smooth and as good as I could have imagined or hoped for. So now, ICFP very quickly in 10 minutes, or maybe less than 10 minutes. You will see I don't have much to say, and so we will have time for other things. So ICFP, International Conference on Functional Programming. So let's focus first, see if I bring my mouse, on the international conference aspect of ICFP. So maybe the first thing you are expecting is some kind of statistics about the numbers of submissions, numbers of acceptation, and these sort of things. So here we are. 114 submissions, 38 accepted, 33% of acceptation, or this is the acceptation rate. So how does it compare with previous years? Well, we are doing exactly or almost perfectly steady in comparison to the previous year regarding ICFP. And if you compare, or if I compared with other major ACM conference about PL, you see that basically we are in the same ballpark as UPSLA is, and maybe not exactly as competitive as PLDI or PUPL, but roughly speaking, same kind of things. But for me, the important aspect is that this year we have really been steady and comparable measure. Initially, I was a little bit worried because ICFP being in the US and all the problems that you know, people from Europe not really willing to come. I was afraid that the numbers of submission will be lower. Well, we have what we were expecting. So this is the numbers of submission. And how do we compare in terms of so acceptation rate with other conferences and the numbers of submissions? And you see that for that, too, we are really steady, same numbers of submission as previous year. And when we compare with the other conferences, still the same, we are significantly smaller. ICFP is smaller. And what you do not see here seems to be a trend for the other conferences where all of a sudden the numbers of submission significantly increase. So it's not really visible in 2025, but it seems to be more significant in 2026. So last year, it was only Uppsala that doubled. So maybe it was because of geographical localization of Uppsala. It was in Singapore. So last year, we have received, I was on the PC of Uppsala last year. So we have received much more submission from China than we were used to. So this, in part, explains the numbers of submission we received. This year, I don't know how Uppsala behave. I don't know how PLDI behaves. What I have been told is that Popl is also more or less doubling the numbers of submissions they have received. We have not observed something like that. I cannot tell if it's a good sign or a bad sign. Maybe it's even a good sign that ICFP remain a relatively small community. We are focused and we have our conference. I don't know. Something that I have not planned to mention is maybe one of the things we were afraid of is because of the explosion of AI, we were wondering if we will be overwhelmed by an AI submitted or written paper, and it happens not to be the case. Well, as far as we can tell, we don't think that we have received many or a significant numbers of papers that have been written by AI. And actually, I think it's an interesting story. We have rejected, on the top of my head, it was something like 5 papers that were apparently written by AI, and the reason why we have rejected them is not because they have been written by AI, but it's just because they were full crap. And they were just incoherent with themselves. That is, they pretend they will be delivering something, and they did not deliver it in the paper. So it was absolutely apparent and obvious that these papers were automatically generated. So this is it for the numbers of submission and the comparison with other conferences. So ICFP, International Conference. What is the international aspect of the conference? So usually we try to gather statistics about the countries where people are submitting from. But you know, I'm French, but I like also to call myself a European. So I'm presenting statistics not by countries, but by continent, and I think it makes sense. So this is the numbers of submission, and this is the numbers of accepted paper. So the first observation that you can make is that, unsurprisingly, we have received no submission from Antarctica. Maybe also unsurprisingly, but this time sadly, we are receiving no submission from Africa. Maybe this is something we should care about. And maybe, I don't know, in one day we could imagine organizing ICFP in Africa. Why not? But anyway, we have not received a submission this year. So the second thing is, as you can see, ICFP is almost a European conference, right? Almost half of the submissions are coming from Europe, and half of the papers that have been accepted are coming from Europe too. And kind of North America and Asia are not strictly on par, but kind of comparable. So I think that the only interest of this statistic is maybe when we are considering where ICFP should take place, and maybe tell us something in between Asia, Europe, North America. That's probably the only thing we can extract from this slide. Okay, the other statistic I have tried to collect is numbers of author per paper. It's not that it's very interesting per se, but it's just a kind of a measure that tells us a little bit what is a typical ICFP paper. You know, you have communities where you have 30, 40 authors per paper. Are we this kind of community or not? So this is the numbers of submission for the submission, and this is the numbers for the accepted papers. And as you can see, 3/4 of the accepted paper have been written by 1 to 4 authors. So it means that, roughly speaking, papers are describing small work or not a work of a large team. So this is the kind of thing we like. And more than half of the paper have been written by at most 3 authors. So it means that it's focused, it's not a description of a large team working for decades on a problem. This is not the kind of paper we are publishing at ICFP. Okay, so this was it for the international conference aspect. So remain, of course, the functional programming aspect. So the topics. And for that one, I have not, strictly speaking, followed the call for paper, but I have applied my personal classifications that you can see on the slide. What are the topics that have been submitted, and what are the topics that have been accepted? So it's very loose and probably not so well defined. It's just my understanding of the thing. So it's kind of arbitrary, if you want. And the interesting aspect for me is that we can see that half of the paper are theoretical papers and half of the paper are kind of practical paper. And I think this is nice. I see this slide as a good sign. We have a nice balance between theory and practice, and I think this is what ICFP is meant for. So for me, this is really something positive. And of course, the statistic you are all waiting for is what are the languages we are using at ICFP. And for this one, I need your help. In your opinion, what is the most widely used programming language at ICFP this year? OCaml? What? Rock? JavaScript. Okay, so this is a slide. This is a slide you discover that also I have been tapped in by JavaScript for a couple of years. I am a true schemer, and I remain a true schemer, because the most language is a no language at all. That is, the numbers of papers that are not even mentioning any programming language, not including any single line of code in the paper. And if you consider the accepted paper, it's even worse. So my advice for next year to submit to ICFP, don't bother with programming languages. So roughly speaking, that's it. And I try to collect other statistics about artifacts, which are the artifacts that I've submitted. And now you see, indeed, it's theorem provers that are kind of leading the thing. And I also try to build some statistics about how numbers of lines of code have been submitted in the artifact. But this is super complicated to evaluate, because some artifacts are just included in a much larger things. So I'm not sure these numbers really mean something. But anyway, at least the artifact community have had to deal with these lines of code, and this gives you an idea of the complexity of the thing. Okay, I think that's it. That's the only thing I have to say. The last slide is for, of course, giving my thanks to all the people that have helped me, and in particular the associate chair, Steve and Robbie, without which I would not have been able to conduct all these things. So thank you very much to everybody.
So now I get a very enjoyable task of presenting some of the awards for our community. So we'll begin with the most influential paper award from ICFP 2016, 10 years ago. So the most influential paper for ICFP 2016 is Higher Order Ghost State by Ralph Young, Robert Krebers, Lars Berkedal, and Derek Dreyer. So the SIGPlan Awards Committee wrote the following citation for this paper. Higher Order Ghost State represents a major milestone for the widely used IRIS program logic framework. Colloquially known as IRIS 2.0, the paper contributes a key feature, the ability to store arbitrary higher-order separation logic predicates in ghost variables. The feature is justified using guarded recursion and a new algebraic structure called cameras, roughly a generalization of partial commutative monoids with a form of step indexing. Higher-order ghost state was later shown to be an essential building block from which other features like impredicative invariance and weakest preconditions could be derived. Its broad and lasting impact is evident in the currently 165 papers that use Iris in some way, including 45 POPL, 29 PLDI, 20 UPSLA, and the most important, 25 ICFP papers. Derek will say a few words.
Thank you very much. If I can just find my notes here. Yes. Sorry, one sec. I, of course, had my notes, and now I don't have them. Sorry, one second. Just the usual technical difficulties. Well, all right. Let's go with this. Thank you very much. It took a while to come up with that. Thank you very much to the award committee and also to the ICFP community for this great honor. My co-authors Ralph, Robert, and Lars unfortunately could not be here today, but it's my pleasure to accept this award and to take the opportunity to say a few words of appreciation on behalf of all the authors. First of all, I want to thank the many contributors to the IRIS project. The ICFP 16 paper was, this ICFP 16 paper was one of the earliest papers on IRIS. So of course it influenced what IRIS became, but IRIS would not have become what IRIS became if it, and it wouldn't have had nearly as much impact if it were not for the subsequent amazing contributions of many, many researchers around the world. I want to give a special shout out to Jacques-Henri Jourdan. Jacques-Henri joined my group at MPI very shortly after we submitted this paper, and he immediately began contributing useful technical insights, one of which even made it with acknowledgement into the final version of the paper itself. And he quickly became one of the lead technical developers of IRIS. The IRIS project has been blessed with many wonderful collaborators like Jacques-Henri. Second, I want to say a few words about the paper itself. Much like the first IRIS paper that we published in POPL 2015, this ICFP 16 paper was very much curiosity-driven research. That's a fancy way of saying that we didn't really know whether what we were doing would be useful or not, but we thought it was cool and we tried to convince the reviewers that it was cool. In particular, we were trying to simplify and unify the foundations of higher order concurrent separation logic so it would be easier to develop new program logics for a wide range of applications. Because goals like that are so open-ended, curiosity-driven research is often hard to write grants about, it's hard to write papers about, but it's been my experience that much of my best work has been curiosity-driven. And I want to thank the SIGPlan conferences, including ICFP, for being such a receptive forum for this kind of work. Lastly, I want to thank ICFP specifically for being inclusive of papers like this, which are, at least superficially, outside the traditional scope of functional programming. It is indeed true that the paper is all about models of logics for stateful reasoning. And in fact, I checked this. This is the first paper to receive a most influential ICFP paper award that has the word state in the title. So I know I should be flagellating myself for this. But at least it has higher order there as well. Okay. But we feel that it is nevertheless spiritually very close to ICFP. The whole point of this paper was to develop more beautiful, reusable abstractions for taming and encapsulating stateful reasoning, motivated by elegance and conceptual clarity, which is at the heart of why many of us care about functional programming. On a personal note, ICFP 2005 in Tallinn, Estonia was the first conference where I had a paper that I published after my PhD. And it was, I still remember vividly being excited about submitting that paper, being excited about getting the paper accepted, being excited about presenting that paper at the conference, and it was also the first conference where I met a bunch of my initial set of collaborators. Over the years, I've continued to submit some of my best work to ICFP and to form friendships with a bunch of great people in this warm and welcoming community. So it's really an honor to receive this award from ICFP. Thank you very much.
So now I have the opportunity to give out another important award. Every year, SIGPlan gives out the Programming Languages Achievement Award to someone who has, over their career, made a major contribution to the entire programming languages community. And the person who receives this award gets to choose where they will receive the award, and this year's recipient chose to receive it here at ICFP. So the 2026 ACM SIGPlan Programming Languages Achievement Award goes to John Hughes of the Chalmers University of Technology. It's very hard to write down what John has done for this community, but the SIGPlan Awards Committee provided this citation. John Hughes has been a leading light in the PL community for decades, known for his contributions to functional programming through the design of Haskell and to software testing through developing QuickCheck and founding QVic. His outstanding leadership has included launching the Journal of Functional Programming, helming WG 2.8, founding the Erlang Workshop, chairing FPCA, speaking at developer conferences, and mentoring many successful students and younger researchers. His work on QuickCheck launched the field of property-based testing, which bridges the gap between formal methods and traditional approaches to testing, giving real developers immense bug-finding power for relatively low cost. PBT has been used to find critical bugs across diverse application areas, including telecommunications, replicated file and key value stores, automotive software, compilers, and blockchain infrastructure. And just to add my own thought, perhaps the best testament that we can offer to John is the number of different papers that we saw yesterday and today that took property-based testing as a fundamental primitive in our research community. So, John has a few slides that he is going to present.
Okay, so this is the award itself, and I want to say that I am very proud and honored to be selected for this award. Thank you very much to the SIGPlan Awards Committee. It's quite delightful. The citation that we just heard mentions a number of nice things, but I think probably the most important is QuickCheck, so I thought I would try to talk a little bit about what I did that has resulted in this. I was going to have a quick introduction to QuickCheck on one slide, but we've seen so many of those today that I thought I would skip it. So where did QuickCheck come from? Well, it might be natural to think that we had a big research project to develop it, but no. We had a big research project to do something else altogether, I forget what. And I have been working very hard on the final report. I remember that. Finally, it was done. And I had a week with no deadlines, a week just to have fun. And I thought I would just play with some ideas. And one of the ideas that I thought would be fun to play with was taking properties and testing them on random data. So I started trying to implement that. And who knocked on my door but Koen Klassen? And he said, "What you up to?" So I showed him my idea, and he got fired up about it. The next day, he had a complete implementation. Although there were some things that I had been thinking about that he hadn't. So he gave me his code. I worked on some more, gave it back to him. The code went to and fro between us for about a week. And at the end of the week, we had essentially the first version of QuickCheck that was in our ICFP paper. A paper which 10 years later won the most influential paper award. And it's actually now the most cited and most downloaded ICFP paper ever. So that's nice. Not bad for a week's work, eh? But we did it for fun. And I think that's partly a strength. Property-based testing is fun. People like doing it. And I think that has helped the idea to spread. But the downside was that we maybe didn't really take the idea seriously enough to begin with. It was 6 years later when we had another big project which was supposed to combine property-based testing with AGDA-style reasoning. And in the middle of this project, our funding agency insisted that we go and present what we were doing to their committee of the great and good from Swedish industry. So we weren't at all sure how this would go, but we prepared a talk, and I started off with a quick QuickCheck demo, and then we spent most of the talk talking about the work we were doing on proofs. In the room was Mike Williams. Mike Williams is one of the 3 designers of Erlang, and by this time, he was heading the software development for Ericsson's 3G radio base station. So that tells you how long ago this was. This was a really big project, about 3,000 developers. And at the end of our presentation, Mike said, go back to that quick check stuff. We want that. And that was the direct reason why we started a company. The funding agency encouraged us very strongly to do that. So Thomas Hartz and I founded Cubic at that point. Cubic is still going. And we started applying property-based testing to industrial projects. I thought I would show you our first important bug. So this was in an Ericsson product for connecting multimedia phone calls. And it's controlled by a protocol that lets you start calls by adding callers. So here we are. I started this test by adding 1 caller. Now, he can't do very much at the moment because there's nobody else in the call. But then you can add another caller, and now they can talk to each other. So that's great. But at this point, the call is full because this product only supported 2 callers per call. So that's it. You can't add any more. What you can do, of course, is subtract a caller. And usually the next thing you would do would be subtract the other caller. But that's not what QuickCheck did. QuickCheck added a 3rd caller. Now the call is full, but QuickCheck subtracted that 3rd caller, added a 4th caller, and then subtracted that 4th caller, and the system crashed. I love this bug. I mean, look at it. We tested add, subtract. It worked once. It worked twice. By induction, it must work any number of times, right? But it doesn't. You do it the 3rd time, and the system crashes. So it's a really weird bug. It's something that nobody would think to write a test for. But it's also minimal. So we found this test case by shrinking a sequence of 160 operations. You can imagine, if we had given Ericsson developers a sequence of 160 operations that crashed their system, they wouldn't have been able to do anything with it. But in this one, each of those operations is relevant. It turns out the crash happened because subtracting a caller corrupted data structures. It's just that that didn't matter if the only thing you did next was throw them away. And that's what a second subtraction would do at that point. But this sequence could reveal that. And this bug really amazed Ericsson's developers. I think it's fair to say that this bug sold QuickCheck to Ericsson. Another early project we did was AUTOSAR testing for Volvo cars. AUTOSAR is a vehicle standard, which, among many other things, specifies what the basic software on processors in cars should do. And there are, however, many different implementations, because every supplier writes their own implementation. And Volvo wanted to be sure that their suppliers were actually following the standard. Because if they don't, and you put hardware from different suppliers together, it might not work. So they hired us to test against the AUTOSAR standard. We read 3,000 pages of PDFs. We turned that into 20,000 lines of QuickCheck code. Not a bad ratio, if you ask me. We tested 1 million lines of C code from 6 different suppliers. And of course, we found lots of problems. Many of them problems in the standard itself. So before we did this project, I think you could perhaps have wondered, does this approach really scale? Well, the answer is yes, it scales. So each of these examples that I've shown you, they required more research. The version of QuickCheck that we had in our first paper was not appropriate for testing this kind of software. It was designed for testing pure functions. Well, guess what? Every system that Ericsson wanted to test had internal state. So we had to do more research to come up with a way of testing that stuff. And we developed a state machine modeling library that has stood us in very good stead and been emulated in virtually every property-based testing library since. For this Volvo cars thing, we had to figure out how to support mocking in property-based tests and how to cluster models together so that, for example, you could write a model for each layer of a protocol and then cluster them and generate tests for the entire protocol stack. So that kind of thing is quite interesting. You will sometimes hear people say that researchers' job is to get the patent. And once you've done that, you don't want researchers running companies. Businesses should be developed by business people. I think for this kind of innovation, that is completely wrong. What was in our paper was not sufficient to go out and do the industrial applications that we did. So I think researchers must be involved in commercializing this kind of complex research. What was the win for the university then? Well, oddly enough, Swedish researchers own their own research results. So the university has no stake in QVIC and never has had. And I know that some universities dream of, owning the patent for the cure to cancer or something and cleaning up big. So we didn't do that. But on the other hand, there was a win for the university. We were able to raise millions of dollars in research funding. You won't believe how much easier it is to get research grants when you have a company of your own to exploit the results. Right now, we have had to write so many exploitation plans, and they have been dramatically easier to write since we had a company of our own. And also, of course, the fact that I was spending a lot of time working with industry meant that I had a lot of contacts to bring in guest lecturers for courses and a lot of industrial input for our teaching. So I think those are the real wins for the university out of all of this. What about wins for me? Well, I've been lucky enough to be able to spend about half my time for most of the last 20 years working for QVIC. Many universities would not permit that, but Chalmers did, which I'm very happy about. And so I've spent an awful lot of time speaking at industry conferences and spreading the ideas. Probably, if I hadn't done this, I would have written more papers. But, I worked with customers. That's very satisfying. And I won an award. That's what I had to say.
Okay, can I ask all of the participants in the student research competition to come up? As they come up, first let me introduce myself. I'm Kimball Germain. I'm one of the co-chairs for the student research competition. My fellow co-chair is Alexandra Moana. And I just want to give you a little overview of what these students did to participate in this competition. They submitted a 3-page abstract, which was reviewed by our program committee, and they could be rejected at that point. Then they came here and they held a poster session yesterday, and they answered questions for a few hours, and then some of you saw their presentations today. So I would like to present to them their awards. So, and there are 2 categories. They're undergraduate and graduate. So second place in the undergraduate category goes to Pablo Benario Figuera for his work Incremental Property-Based Testing. First place in the undergraduate category goes to Ivan Mladenov for his work Quicker Chick. Third place in the graduate category goes to Vincent Chan for his work Better Safe and Sorry, Tabular Types for Dynamic Languages. Second place in the graduate category goes to Aryan Prakash for his work Coverage Types Modulo Equivalences. And first place in the graduate category goes to Victor Dang for his work JavaScript Regular Expression Matching is P-Space Complete. I know you just clapped a lot. I would just like to ask for one more round of applause to thank all of the participants, all of the members of the program committee, and for those who put on this conference. Thank you.
me again. Good. All right. Hi, everyone. Yeah, I just kind of take a few minutes of your time to tell you a bit about some recent changes to JFP, the Journal of Functional Programming. In case you don't know already, Journal of Functional Programming, JFP, is one of the leading journals in programming languages since 1991. Gabrielle Keller and myself are the editors-in-chief, and I think if you aren't currently working on writing journal articles, you should start thinking about it, because I think, at least in my experience, it's been, when I've worked on journal articles, it's been some of the most satisfying experiences I've had in publishing papers. It gives me a chance to explore ideas at much more depth and also write the kind of articles that don't necessarily fit into our conferences. There are two kind of general paths for most JFP articles. This is all sort of review. I'll get to the new stuff in a second. There's two basic paths. The journal first path is where you publish an article directly in JFP, and then you have the opportunity to give a talk at ICFP in person. You saw one example of that on the first day of the conference. This is only intended for fresh journal submissions, meaning papers that were not previously in a conference or where there was not some previous version of the paper in a conference. But we have quite a few of these every year, and yeah, we encourage these kind of submissions. The other style that's very common is extended versions of conference papers, and in fact, we have special issues ongoing for a number of conferences, including ICFP, but also currently also Popl and Uppsala. I think this is a great opportunity to take a paper you've written maybe a few years later and combined with other papers and present an extended, revised, and rethought version of your work. Actually, in fact, the paper that I got the award for earlier is an example of that. That was a paper. Well, the journal paper we wrote afterwards is an example of that. So that was a paper that was published in ICFP, and we were asked to do an extended version. We actually combined that with another paper that we had written in ESOP and brought them together, and then significantly extended that. And that's been one of my most cited papers, is the resulting JFP paper on Iris. So anyway. This is all just sort of some background on JFP. The thing I want to tell you, in case you haven't heard already, I did talk about this last year's ICFP in Singapore, and I also gave a presentation at Popl this year, but many of you may not have heard, is that JFP used to be published by Cambridge University Press. A few years ago, Cambridge University Press switched to gold open access, which was a very positive move, but that still meant significant article processing fees for authors. So for various reasons, in the last year, we've actually switched our publishing platform. We transitioned to publication through EP Sciences, which is a publication platform that handles a number of different journals. It's funded by the French government, and it supports diamond open access. So that means there's no fees for authors or readers, yeah, it's completely free. It is an overlay journal. That means that people, to submit to the journal, you submit a paper on one of various paper archives like Archive, HAL, Zenodo. Those are the three that we support. And then you submit the paper to the journal. And in the end, the paper is published on one of those open access archives, but with a sort of seal of approval from JFP, and it's listed on the JFP website and indexed as part of the journal. A side benefit, I think that's a good thing by itself. I'm a big fan of diamond open access. But a side benefit is that we also have had, since moving away from Cambridge University Press, we have more freedom and control over various aspects of the journal. The main one that we've exercised during our transitional period was to create a new LaTeX style file, finally. We were never a huge fan of the old one. So we moved to a new one that looks largely similar to the old JFP style, but is compatible with ACM Art, which is the PACMPL style file. And so you can basically more or less take if you have an extended version of a PACMPL paper, like an ICFP paper, you can just recompile it and it'll look like a JFP paper. To give you a little example of that, here's just two randomly selected papers, one from the old style, from the old JFP style, and one from the new one. They look pretty similar. So it's it should hopefully be a very easy process. And you can find the new style file on the JFP website. Speaking of which, here's the JFP website. You can find this, you don't have to write down this URL. If you Google for Journal of Functional Programming, I think this comes up as the second link. The old website, of course, is still the first one, although the old one at least does have a redirect to this website. Yeah. It's up, it's running. We have there's been a lot of work in getting it up and running, but we now have a number of articles up there where we have a lot of papers in the queue. And what I wanted to ask you is, so what does this mean for you? One is, please keep submitting to JFP. We are getting regular submissions, and we are going to continue doing our special issues for SIGPlan conferences. But we were paused for a few months at the very beginning of the year where there was no submissions, but since March we've been actively processing submissions, and now we sort of got the hang of this new system. The EpiSciences system is actually, the people at EpiSciences are really helpful. Yeah, I won't say in contrast to what, but they're really helpful, and so that's great. But there's always kinks to iron out of any new system. So, but things are going, I think, pretty smoothly now. One thing, however, is that we are very low budget. So it's Diamond Open Access, so we're not receiving any money, which is fine from authors or from readers or anything. So right now, there's no support for example, there's no support for copy or layout editing, which for my money was a plus. With the old JFP, there were often many authors who were unhappy with their copy editing. But we are doing a little bit, we were doing sort of a cursory check on papers myself. But we would be happy to get support for things like that from volunteers in the community, and we do have some initial funding to draw from, thanks to Jane Street support. Thank you, Jane Street, for supporting Journal of Functional Programming. But yeah, I just want to say, put it out there, if you are interested in contributing to helping the administration of the journal, helping with copy editing or things like that, just let me know. Thank you very much.
All right, I'm Steve Zdanswick from the University of Pennsylvania with an announcement about next year's ICFP that you've all been waiting for. If we can switch to, I will be the program chair, and Robert Krebers will be the general chair, and he'll be organizing it at Nijmegen in the Netherlands. Robert couldn't be here today, so he prepared this very short video that I'm going to play. Let's hope it works.
Hello all, I'm Robert Krebers from Radboud University Nijmegen. Hello all, I'm Robert Krebers from Radboud University Nijmegen. I will be the general chair of the next ICFP, which will take place in Nijmegen, the Netherlands. The PC chair will be Steve Zdanswick from University of Pennsylvania, United States. The conference will take place from 26 September until 1st of October. The main conference will be on Monday, Tuesday and Wednesday, and the co-located events will be on Sunday, Thursday and Friday. So, Nijmegen, the Netherlands, where is that? Well, the Netherlands is a small-ish country located in Europe. Nijmegen is a city in the middle, close to the border with Germany. Some things about Nijmegen. Nijmegen is often claimed to be the oldest city of the center, hence has a nice historic city center. Nijmegen is also the place where the mighty river, the Rhine, turns into the Waal. Nijmegen is a vibrant student city, home of Radboud University. In Nijmegen there are many nice places to eat and drink. I would particularly recommend the Nieuwe Winkel. It's a 2 Michelin star vegan restaurant, very expensive, and you need to reserve well in advance. And Café Jos, which has more than 200 special beers. Of course, there are many other options if you don't like expensive vegan food or special beers. The Netherlands is also well known for functional programming. The purely functional languages Clean and Nix have been developed in the Netherlands. Also at universities throughout the Netherlands, there have been many contributions to Haskell, ROC, and ACTA. The Netherlands is also well known for the theory of functional programming. Particularly, there is the famous The Lambda Calculus book by Henk Barendrecht, who is an emeritus professor at Radboud University, Nijmegen. ICFP will take in the Van der Valk Hotel. We will have the entire conference floor of the hotel for the whole week just for ICFP. This includes a big conference room which can host up to 400 persons. The conference room can be split into smaller rooms that we can also use it for the co-located events. There are also various smaller conference rooms that we can use for smaller co-located events. Adjacent to the conference room, there's a lobby where you can get plenty of coffee, tea, and other drinks throughout the day. Also adjacent to the lobby, there are various spots and smaller rooms where you can have meetings or you can network with your fellow researchers. The venue is a hotel, and it has about 116 hotel rooms. You can, of course, also stay at other places. So the venue is located right next to a train station. It takes about 3 minutes to get to the Nijmegen Central Station and 13 minutes to get to the Arnhem Central Station. Instead of taking the train to Nijmegen Central, I would also recommend to walk over the river. It's a short but beautiful walk. In Nijmegen and Arnhem, there are plenty of affordable hotel rooms. However, there are not as many as you would expect in a capital like Indianapolis. That means you should book your hotel early, probably at the moment you know your paper got accepted or you're sure that you want to attend the conference. Nijmegen is well reachable both by air and by train. So by air, the two closest and biggest airports are Schiphol and Düsseldorf. Schiphol takes about 1 hour 50 by direct train to the venue, and Düsseldorf 2 hours 10 by train to the venue. There are also many smaller airports like Eindhoven and Rotterdam in the Netherlands and Weeze in Germany. By train, you can go to Arnhem in 13 minutes. From there you can get your connections to Germany, Denmark, Austria, Switzerland and so on. Or you can go to Rotterdam in 1 hour 40, and there you can get your connections to Belgium, France, the UK and so on. So, I am looking forward to see you all in Nijmegen next year, and I wish you a very pleasant ICFP this year.
I have one more slide. I thought I would add a little bit of detail. So I look forward to working with Robert to put together a great ICFP for you next year. I wanted to give you a few more details about the timeline and the call for papers, which are available. First, I want to thank Eric Tonter, who from the University of Chile, who's going to be the Associate PC Chair. If you have any questions, you can contact both of us at the mail list that's up there. The submission deadline is similar to past ICFPs. It landed on Thursday, February 25th, 2027. You should submit all of the kinds of papers that we love to see here at ICFP, especially those that include programming languages in the papers themselves. But we'll also welcome functional programming, functional Perls, and experience reports. I wanted to call out a couple of changes to the call for papers. First of all, there's a new ACM policy about AI usage. Basically, the directive is you're welcome to use AI however you like in preparing your papers or doing your research, but you should just explain what you're doing in the context of your paper in the same way that you would explain experimental method and evaluation. You can see the details about the ACM policy and our advice about how to use it for ICFP on the call for papers. We're not sure whether we will get a big increase in submissions. As Manuel was mentioning, other conferences have. So I've decided to put into place the reserve reviewer policy. Hopefully we won't need that. That basically will give us a little bit of a buffer in case we get more papers than we expect. And I've given some advice about supplying mechanized proofs, which are becoming more important as part of the supplementary material rather than deferring to artifact evaluation. You can see all of the details on ICFP27 sigplan.org. And I just wanted to conclude by thanking in advance all of these people who will be helping to evaluate your papers should you submit on the program committee for next year. I look forward working with them and seeing all of you next year in Nijmegen. Thanks.
Hello, my name is Nolan Royalty. Oh, that's not what you want to see. Okay, excellent. So, my name is Nolan Royalty, and I was the lead for this year's ICFP programming contest, the 29th annual programming contest. I'm here to tell you about it. And I should acknowledge up front that I am representing a team of 4 people. So my good friends Elliot Hedeman, Henry Nelson, and Frank Chiaroli Jr., who are all back in New York working on other things, were key developers of this as well. So the question that we had for teams for this contest, the task that we gave them was around the idea of how a computer works. And I think maybe the answer that we gave will be familiar to some of you. I think it was a surprise to a lot of the teams. That answer, of course, is that there are millions of little men inside your computer that are running around physically executing instructions. And we taught all of this information to hundreds of teams with the use of a textbook that had a full kind of in-universe explanation of this ridiculous programming language, as well as a series of increasingly difficult problem sets. So the language that we designed this year is a 2D visual language with a full editor and debugger that had like time travel debugging, all provided by us. So I'm going to give you kind of a whirlwind tour of that language. I'm skipping, I think, over half of the instructions in the language. I'm not trying to make you proficient programmers in this language. I'm just trying to give you a sense of the types of problems that teams had to solve. So at a high level, this was a 2D visual language with little men represented in red @ symbols. Little men are confined to these blue rectangular rooms. They're always rectangles. And they move through space and time. You can see this man hitting a wall, which is an error. And below, you can see the man being redirected in a loop using various different angle brackets, things like that. That is kind of how you established control flow in this language. To do an instruction, to perform anything, you need to run over the instruction, the simplest instruction being H, which halts an individual little man. And much like many humans, the little men have 2 hands, registers that can hold 64-bit integers, as well as a backpack, which was kind of a pseudo-register or loop counter. You could put a value into that backpack, and you could decrement it, and you could ask, is this value 0? But you couldn't extract the value from it, preventing you from having the flexibility of a full 3rd register. The result of this is that an individual program written in one of these rooms was not very expressive. The program here has operations for putting like a number, like 4, into a man's hand. M copies a value between 2 registers. W swaps those 2 registers, etc. So those are some of the basic primitives of the language. So since individual rooms were not very powerful, we gave teams the ability to communicate between different rooms by drawing these physical pipes that data could travel in. We had send and receive operations that were these blocking operations that broadcast something in a man's hand to another one. You can see that here, and you can maybe see that it takes time for data to travel over these pipes. So the kind of closer you put your rooms together, the faster your program ran, just like real computers. Additionally, many of these operations target the nearest pipe. So you can maybe see as I click on different S's on the screen, different pipes are highlighted. And this is absolutely miserable because it means that if you refactor your program, you can end up sending data to the wrong room, which is utterly impossible to debug. So a lot of fun. Additionally, of course, we had input and output. It would be bizarre to have a language where input or output was difficult. So input and output was just kind of rooms connected to via pipes like anything else. This program takes in the number 42 from input and outputs it to standard output. And control flow in this language works by conditionally turning in different directions. So the X operation here on screen turns you left, right, or makes you go straight, depending on whether your first register is negative, positive, or 0. So you need to kind of create these like 2D, like linked together structures if you want to do something like loop. We also had displays within the language, which we called the LM75. These allowed teams to dynamically draw images to these fixed-size displays during the contest, and we graded them on their ability to draw on these displays. Frank, one of the other people on the team, worked really hard on this and modeled the API here after old like physical hardware, which is really cool. No time to get into all of it, but you have to attach 3 different pipes in different places that do different things. It was a lot of fun. And we had a bunch of inspirations for this. Bufunge, which is a 2D grid-based SOLang that I think some people may be familiar with, was a big one. It has a similar idea of a physical program counter moving through space. TIS 100, which is a programming game from the excellent Zachtronics game studio. It similarly has many very weak programs that need to do a lot of communication in order to get things done. And Zachtronics has built a lot of programming games that we took inspiration from the way that judging works in those games as well. And finally, there's this more obscure language called Little Man Computer that's a more serious language than you might guess, but really leans into kind of the metaphorical idea of people moving through a machine, which is where we got the original idea from. We also thought a whole lot about designing a contest in a year of agentic programming. We decided up front that banning AI would be roughly impossible to enforce, and so we wanted to instead design a contest that was still fun for teams in a world with agents and wasn't trivialized by them. One big way that we did that was by placing this heavy emphasis on spatial reasoning within the language. Agents do still struggle to read this code since you need to be able to read it front to back, up and down, reason about what is close to what. And so agents are really good at writing code that writes this code, but adding that indirection layer, I think, did place people on a more level playing field. The other thing that we did was that we chose to provide a ton of tooling to teams up front. The idea there was that some teams would probably want to not use AI during this contest. That's an utterly reasonable thing to do. Programming is fun. But AI is phenomenal at providing like disposable development tooling. And so by providing an editor and a debugger, we thought we could level the playing field a bit. We provided teams 16 problems across 4 problem sets, with the 4th problem set released 24 hours into the contest after the lightning round ended. The easiest problem was to compute the nth triangular number, and the hardest problem was to implement a subset of the Little Man language inside Little Man and then display running programs on our display. We called this Little Man, or LLM. Problems look something like this, so a relatively small spec, a relatively detailed description of the input and output. And the way that judging worked is that we provided teams a bunch of public test cases. So here is exactly what data you'll receive. Here is what data you need to output given that. You could run in our online editor against all of those test cases and evaluate your program. And then on submission, you would be evaluated against a separate hidden set of test cases and judged on your performance across all of those tests. This just prevents teams from hard coding public test data. We judged teams based on looking at the physical size of their programs, taking the maximum of the width and height of a program and squaring it, and then multiplying that by the number of ticks a program took, where a tick advances all little men across all rooms. Parallelism in this language is free. We chose to do this because we observed that originally folks during testing would write these really long programs, and that was kind of ugly, and we thought this would produce like more interesting programs to show you now, which it did. And also because it's another way of placing emphasis on spatial reasoning. We gave teams up to a point for completing all the tests, and another point using kind of a board account, where you get a point if you're number 1 and 0 points if you're in last. Over 250 teams scored points, which we were really excited about. I think the barrier to entry was relatively low here. So since this is a visual programming language, I thought it'd be fun to show a couple of the programs that teams wrote. So to start, one early problem was to reverse a list, and this was the first solution that was able to reverse a list at all. It's really slow, it's n squared. You can see down at the bottom we have like a pipe that's being used for storage, and we're kind of looping through that. 24 hours in, this was the most efficient program. This is sorting twice as much data, and it is substantially faster. You can see that we kind of write all of the data in and then read it out backwards. But 24 hours in, we introduced this new instruction that we called split, which is basically fork. It takes one little man and splits it into 2, preserving register state across both of those. And we weren't actually really sure what teams were going to do with this, but one thing that teams found was that this was a way to add some level of dynamic memory allocation to the language if you were extraordinarily careful. So an example of being extraordinarily careful is here with the final reverse winner at the end of the contest, where we're just kind of dynamically allocating more and more little guys and then making sure that they emit data at exactly the right time. A fun example of kind of our scoring function is that this was the winning solution to matrix multiplication. And I like this partially because matrix multiplication is the classic embarrassingly parallel problem, and we have free parallelism in this language. But because we so heavily reward compactness, you see something like this instead of kind of splitting that computation over a much wider set of rooms. I think it's kind of debatable whether we over-rewarded compactness, but we certainly got squares. One of the problems that we gave to teams was what we called history lesson, and we graded this differently. We said that you could be as slow as you wanted. The only thing that you had to do was make the smallest possible program. And what we asked teams to do was emit in ASCII the location of every ICFP going back to the start, as well as the most influential paper if named, and the names of the authors of that paper. And we got 3 different tied winning solutions. These are all 76 by 76. One is like an order of magnitude faster than another one, which is kind of bizarre. Maybe there's some information theory interesting thing there. I don't really know. But all of these gray blobs are just literals that teams are embedding inside these programs. I think they came up with really efficient dictionaries that were good at memorizing all sorts of different relevant names with a heavy emphasis on names like Simon and Peyton. And we also had an 142-way tie for our easiest problem of generating triangular numbers. There are 2 different kind of the rotationally equivalent answers here. We published really detailed information on the scores on our leaderboards, so you could kind of reverse engineer by prime factoring the footprint of the winning solution, which I think allowed a lot of teams to come up with something like this. A couple more here. I'm going to show you a couple of problems that use displays. Here is Unagi implementing Bresenham's line drawing algorithm to draw a clock. And here is an implementation of Snake, where we tell you what's going on inside this game of Snake, and then you need to play Snake on it. The programs are going to get bigger and bigger, so it's going to be hard to show you them fully on the screen. That'll come up in a second. Here's an implementation of a pathfinding algorithm, which I truly cannot show you the display on, but up close that looks something like this. You can see the green dot seeking the red one, avoiding the white walls. And finally, the winning solution to Little Man, which is an implementation of most of the Little Man programming language within Little Man, looks something like this. We'll talk more about this solution in a second, but here it is running, and there's our Little Man program inside Little Man. So a couple of observations from top teams. There was heavy agentic usage across the board, and most teams did check in a lot of the instructions that they were feeding to agents, some of their transcripts, etc. But I think it was harder for us to understand the approach that teams took than it might have been in past years, and the approach that teams took to individual problems might have been more bespoke than you would have seen in years past. Almost all teams came up with a one-dimensional DSL for our language with a separate routing step for connecting up rooms, and many teams built custom editor tooling. One thing we didn't include in our online editor was semantic-aware rotation, since you need to remap glyphs when rotating things. We also saw tons and tons of human hand-optimized code, even on teams that were heavily generating things with agents, because humans are still better at a lot of the spatial and reasoning components that go into this. We also made a few mistakes. I think we had too many problems, which rewarded kind of a spray and pray approach, using agents to get something working across everything. I regret the amount of information that we leaked via leaderboards. I think that allowed too many different solutions to converge to the same approach, because you could reverse engineer the optimal one from the information we provided. And we had a bunch of bugs in our parser, way more than I expected, many of which teams abused, and one of which we found too late, and so we couldn't fix it because it would have broken a lot of winning solutions. So, getting on to the results, we'd like to start by declaring that Lambda Quakens are an extremely cool bunch of hackers. Lambda Quakens were the folks that generated this program, the best solution to the hardest problem. And when they submitted this, it was maybe halfway through the contest, and this scored something like 50 times better than the next solution. It was so much better than everything else that we thought we had like a bug in our infrastructure, or they had like reverse engineered our private test data. But instead, what they've done is that the whole top thing here is just a bunch of int literals. They've come up representing opcodes in a language that they've designed to solve this problem. And the bottom is a computer that they've built with like a CPU and like a bunch of memory units. And they're running the program that they've written inside their language, which they invented to simulate our language, where we're asking them to simulate a subset of our language. We thought this was extraordinarily cool. They did optimize their solution a little more, but I think only one other team was even able to approach what they were doing by the end. But in addition to that, they also answered a question that I'm sure someone in this room is wondering, which is, yes, you can run Doom inside the little man programming language. Moving on, we would like to declare that Rust is very suitable for rapid prototyping. Congratulations to Digital Experts for winning the lightning round, the first 24 hours of the contest. But I'd like to mention that purely functional networks and Kumanami were within 1/10 of a point out of 24 available points at the end of the lightning round. Things were extraordinarily close. Moving on, we'd like to declare that, in addition, Rust is also not too shabby. Congratulations to Toomer for 3rd place for the full contest. In, I think, a new thing for ICFP's programming contest, we'd like to declare that Japanese is a fine programming tool for many applications. Where I think Heuristic Arts acknowledging that they are writing a little bit less of their code by hand this year. Congratulations, Heuristic Arts. And we'd like to declare that Rust and Hexagony, their original submitted language, is the programming tool of choice for discerning hackers. Congratulations to Digital Experts. And that's all I've got. These are the winning teams. Thank you to Elliot, Henry, and Frank, my co-collaborators on this, as well as Doug, Willie, Edna, and Vincent for testing, and to my old programming instructor, Richard Eisenberg, for roping me into running this contest.
This is the hardest job to find someone to do. And I think the reason for that is that everyone who does it goes so far above and beyond what could possibly be expected. And Nolan is another entry in that fine tradition. So thank you very much. That's all, folks. See you tomorrow.